Okay, so we've looked at single user applications. That's what you've done in your assignment. And we've tried to look at how they're implemented. We've described it informally, and now we describe those algorithms more formally using the trace steps. Okay, so let's go through this same series of steps for collaborative applications, and that's the rest of the course. So very high level. And so the idea here is you want to go from single user applications such as Word to collaborative applications such as Google Docs. Well, maybe you won't implement a full Google Docs here, but certainly we want to be able to go at least from our echoer to our IM tool. Okay, in the echoing tool, all input was provided by one user, and I wonder if I got the right display here. And this is being provided by multiple users because you see Alice, Bob, and Kathy. Okay. The reason I'm a little confused that this should have been in green, so I don't know where I got the display from. These both should have been in green. Okay. If you want to run these demos, and when you get the package stuff working, the way to do it is that you look. I mean, the code is big, and you may not be able to find the stuff. But this particular demo that I showed you is executed by this particular class, and you can run the class itself, and then you get these funny consoles that I create. But what you can also do is look at these 4 classes that are in the main that are returned by main classes method. There's a main classes method in all of these packages, and just go to each of these classes and just execute them just execute the mains in them one at a time. Okay, so you go and execute this particular class first using Eclipse. You don't have to use my console here. That's good for demoing and testing. I'm not sure it's good for demoing. I'm not sure it's really good for testing and debugging. Okay, so I don't encourage you to use it. This is something I created just so that I can create a good demo. So go to this particular class, run the main in it, then go to this particular class, run the main in it, and so forth. And these classes are all listed right here. Okay, you'll have to follow the code to figure out. It's just a detail. You can, of course, use my launcher and do execute all. Okay, or you can run it class from the programming. Okay, so we want to not talk about these details. We want to talk about high-level concepts. And the high-level concept we saw so far for single-user application was that there's an architecture. Okay, there's a model, there's interactor, and you can have multiple interactors talking to a model. The model can have submodels, the interactor can have sub-interactors, but this is the basic concept. So that is the anatomy I was talking about, and you can talk of this as the architecture. You know, we guys in computer science use the word architecture a lot. Okay, and we want to now figure out for the multi-user collaborative distributed case, what is the anatomy and architecture? Okay, and so when we talk of architecture, what do we really mean in computer science? So we think architecture of a program. So what do we mean by an architecture of a program? We can talk of architecture as in the hardware architecture also. Let's talk of software architecture. So the architecture of a piece of software or program is some general buzzwords. You don't do any.
The relationship between the classes and objects of the program.
Okay. So it's the program components first and their relationship. Okay. And what are the program components? Classes and objects. So components we can say are maybe the objects. In an object-oriented program, you know, they're also static classes, but ultimately it's the objects that we create. Okay? Can you think of other kinds of components when you go to the distributed scenario that are of interest? So this is for any software. When you go to distributed software, are there some other kinds of components that you might be interested in? Which could be described as the architecture. So can you think of a distributed architecture, and what would that mean? So when you go, yeah.
The components would be different systems, and their interaction
So the different systems meaning different computers?
Yes.
And the computers talk to each other how? What entity on the computers really talk to each other? What's the abstraction on a computer that talks to another abstraction?
Client server reports.
Clients and servers are what? Examples of? So the clients and servers are ports. So ports are what clients and servers use to communicate with each other. Is every distributed program a client-server program?
Or P2P.
P2P. So the peer and the client and the server are what? Are they a piece of hardware? Are they a piece of software? What are they?
A magical abstraction.
Well, that magical abstraction you guys all know about. Even somebody who's Comp 101, not even done programming, should know about that. What's that? What runs on your computer?
Application.
Application, or if you're an operating system person, you might call it a process. Okay. So what you really have are processes on your computer that talk to each other. And depending on the relationship among these, they may be client-server or they may be peer-to-peer. Okay? So we know that in a collaborative program, there are multiple users associated, right? U1, U2, U3. We know that there must be some process. So if one guy is inputting, there must be some process on that computer that takes that input. The hardware cannot send automatically to another hardware the event. It has to send it to a process which goes and sends it to another process. Okay? And we know there has to be some process on the other computers that displays the output. We know that for sure. These processes could do other things also, and there may be other processes also in the system. There may be this other magical process we don't know about that also exists. Okay? So so when we go and look at the architecture of a collaborative program, we have to talk about the various processes involved, and then within the process we have to talk about the objects involved. Okay? And there's a third thing also, that there can be multiple processes on one computer, and so these processes can be mapped to computers in arbitrary ways. In fact, in your demos and tests, you'll be running all of those processes on one machine. Okay? It's just painful to go and find multiple machines to do that. Okay? So, and these processes may talk to each other directly or through some intermediate processes. So this architecture is not saying anything beyond that. This is sort of saying the minimal thing, that you have to have some input processing and some output processing if you're going to input and output, input and view things. Okay? So, and like I said, even if you use the computer, you've probably hit Control-Alt-Delete, and there's a task manager, and it goes in, and you see it uses the technical word processes. Okay, so what's the difference between application and process? Microsoft thinks there's a difference.
An application can have multiple processes.
So you can have, the application may be Word and PowerPoint, and the Word there may be multiple instances of. It's an execution instance, okay? So process is created by the operating system each time a program, which in Java is a program with a main method, is run. Okay, so when I was double-clicking or when I was saying execute all, I was saying please fork or create so many processes, okay, one for each of these programs. Okay? So same program may be executed multiple times to create multiple processes. So now we talk of three kinds of architectures. We talk of the architecture within a process. These green things are objects or classes. Okay, and that's going to be important. Okay. So object architecture describes the objects and communication among these objects in a process. Then we talk of the process architecture. Okay. And the process architecture doesn't imply a distributed program because they may all be on one machine. Now it has the essence of a distributed program. Okay, in fact, the program doesn't have to even change to run it all on one computer or run it on multiple computers. And then, so then you map the processes to computers and say, okay, these two guys run on this computer, these two guys, this one runs on this computer. Okay, so there's three kinds of components here. There's three kinds of architectures at least. Okay. So like I said, in our demos and testing, we will map them all to one machine. Okay. So how do we go from our model interactive architecture which is single user, to a collaborative multi-user architecture. Anybody want to go and look at this architecture and extend it to the multi-user case? Telling me what the processes are and what the communication among these processes may be? Yeah.
Are we talking about peer-to-peer or a client?
I don't know. Say some. Give me some alternative. Something give me the simplest answer first. And who knows what simple really means? What you think is the simplest. And something that may not require any change to your program, or minimal changes to your program, let's put it that way.
Somehow put more interactors up to that model.
I already have 2 interactors.
And the other ones listen to it directly through some abstraction.
So, okay. So tell me the processes. How many processes will I have? Supposing I have 2 users. How many processes will I have in your architecture that you have in your mind? Sorry? At least 2. That's good, that's good. I mean, that's a very strong statement. I mean, it's a very correct statement. It may not be the strongest statement possible, but it's a... And when we go to 3 users, it'll be, okay, at least 2. Okay? At least n, if n is the number of users. And so which objects will be on each. So let's take the 2 case. So Alice and Bob. Alice has an interactor. Bob has an interactor. And where's the model? But it's got to be in some process, right? Okay, so what does shared mean? That's a very good question. And that's where he said client to client and peer to peer also. But there's all these dimensions. I mean, I'm opening a whole can of worms here by asking this open-ended question. That's why I said simple, hard, not, don't change so much. But is it on Alice's computer, Bob's computer, or another computer? Or any of these cases? Right? If it's on all of them, then it's getting a little complicated. Because there's one model. How can it be on multiple machines? Right? What does that really mean? So that to me is a little complicated. But maybe that's what it is too. Maybe it's replicated. In fact, in your implementation, it'll be on all of them. Okay? But if I want to make the fewest edits to this picture, this is what I would do. Put the model on one machine. Okay? It could be a third machine somewhere, or it could be the first user who started the collaboration. It could be on that person's machine. Okay? Put an interactor on one user's machine, put another interactor on another user's machine, and we have 3 processes. Okay? I had to, again, in terms of edits to my PowerPoint, this was the easiest. Okay? And what about these blue lines? Will they change in any way? Do I have to recode? I have to do something different. I'll have to create now three JVMs. One JVM has the model, and each of the other JVMs has an interactor, or multiple interactors maybe. Okay, has some set of interactors. Okay. So I do that, but do I have to change the model or the interactor in any way? Intuitively, they're going distributed. But do we have an abstraction that you guys might be familiar with that perhaps doesn't require me to change my code? IPC. So IPC might mean sockets. If IPC means sockets, then I have to change my code because my previous code had no sockets. But IPC could also mean something higher level that you might be familiar with. Remote procedure call, or remote method invocation in object-oriented languages. So anyone used RMI here? One person? So the idea behind remote procedure call is that You should be able to call a procedure from an object on one machine to an object on another machine. And that call should look identical. Look, it may not behave identical to the call on the local object. That is the ultimate goal of RPC or RMI. If RMI, why? So no?
Well, yeah, it's the goal.
Okay, so where does it fail?
It generally, in order to get the same kind of performance and interaction characteristics across, when it's local or when it's remote, you generally kind of pull your run times up to like the highest of those.
So you're saying that the performance may be worse if you're oblivious to all distribution details. Generally, that should happen, right? If you don't do work, serves you right if you get bad performance. Does it even work? I mean, is it really true that they're transparent? What can be different semantically between making a remote call and a local call? If I make a local call from method object A to object B, yeah.
If I make a local call from object A to object B, I might pass a parameter that is a pointer to an object on my machine. And if we just send that pointer over to something running on another computer, that's worthless. Okay, so there are some semantic issues about what happens when you send pointers. And some languages say you can't send pointers, and some languages say we'll construct the whole graph to which the pointer points, and we'll recreate that at the other end. And some languages, Java says that, we'll send you a remote pointer, which means that we'll send you a pointer that when you refer to that pointer, you'll make a call back to the previous. So that's one difference. Can you think of other differences? Is it possible in the local case for object A to die and object B to not die? For object B to be unavailable while object A is unavailable? I mean, and that happens when the process dies. So in the local case, if the process containing A died, the process containing B also died. In the remote case, one may be alive and the other guy might fail. And when the other guy might fail, we have to have timeouts of some kind and say, either I couldn't reach him or reach it, or it failed. Okay, so RMI is not that transparent because you have to worry about special kinds of exceptions called remote exceptions. Okay, so we might want to just do this. We might want to replace local calls with transparent remote calls, but they are not that transparent. Must deal with communication and failure errors. Okay, plus if you want performance, and that's the big deal here, that in our case we have to make a round trip call. And the caller has to go and wait till that call finishes. And if you don't create special threads, that creates a real performance issue. Okay? So, and our original program was not creating threads. So if I just go in this direction, I'm going to be hosed when it comes to performance. Okay? And there's a central bottleneck. It may not be available. The model machine contain the model fails and your program stops. Okay, so the classic problems of centralization. And of course, in general, you want awareness in the program so that there's awareness in the user interface. Alice should know that Bob has joined the conversation. Alice might want to also know that Bob provided this input. If I just build this program transparently like this, all input is considered equivalent. Okay, there's no knowledge in the model about other interactors. There's no knowledge about the interactors of other interactors, and the communication system doesn't know about the identities either. So no one has that information. So yes, this might be an interesting architecture. In fact, I think this is a very good architecture. If you could build transparent RPC, you can just easily migrate to a collaborative program. Okay, but it has problems. And here's another problem. The sharing is at the model level. Okay, if I scroll within my text box, that is an event that is not of interest to the model. It never goes to the model. what an interactor receives from another interactor is what the first interactor sent to the model, right? So you don't get anything from another user that is something the model is not interested in. If the model is not interested in scroll events, you don't get scroll events. So you will not be able to implement your shared window abstraction using this architecture. Okay, so this is a nice, like this has. I mean, again, in many cases it applies, and when it applies, it'll be great to automate it. Okay, but there are interesting cases, including our assignment, where it doesn't apply. Okay, so architecture is too constrained. Okay, and if we want a more general architecture, then we pretty much have to go to this architecture. Okay, where we say, look, there are some processes on machines, they do input-output, and there's some other processes also, and somehow the input of one person is communicated as output of other processes, and we make no statements about how that happens. That's where you use distributed computing abstractions, and it's all unconstrained. Okay, so this is the most general case, and that is a fairly constrained case. Okay, and what we would like to do is find cases between these two extremes. Okay, if I just go and leave it here, I'm pretty much saying that go study distributed computing, and I have nothing more to add to that. If I leave it at the other end, I'll spend a couple of lectures, show you how you can automate it, but we are done. Okay, so what's going to make things interesting for us is to find a family of architectures between this most general architecture and that particular constraint architecture. Okay, so next time we'll look at an architecture that is little, in theory, less constrained, more constrained than this one, but in practice, I believe, just fine. Okay? Given the set of applications that people have built so far, and that is the architecture supported by the library that I'm giving you. Okay, so before you can, and that is the library you will use for your next assignment. So I need to talk about that very quickly. Okay, and so. If you need to keep busy between now and next Monday, at least do the tracing stuff. Okay? And I'll go and change the jar file this weekend. I have a paper due on Friday night, so I might not get to it. And I suspect that you guys are going to be, you guys have been busy enough trying to finish the assignment by tonight. So, and maybe it's going to take me. Maybe I'll post the library before that also. But by this weekend I'll do it. Okay. Any other issues before we stop? Okay. Okay. And the abstraction layers can be put in the following, can be shown here. There's windows, okay, where we'll see exactly what a window is, but there's a window abstraction. I kept using the word shared windows, and I was using the windows in a technical way. So you can create just windows, or you can, and so then you have a window-based or graphics interactor. Okay. Or you can put some layer above windows, which are special kinds of windows, which we'll call widgets. Okay, text component, button, slider, and so forth. And now the applications you build are either toolkit based or GUI apps. Okay, or you can say I'm going to put a particular console text component on top of this. Okay, and on top of which. And then we have a console-based interactor. Okay, so there are 3 levels of abstraction here, and you also see that there's a little. Why do you have 3 levels? There's a trade-off you have to often make between automation and flexibility when you design a system. Do you try to support a large range of applications? If you do that, you make very few decisions about the applications. So you're flexible, but because you made very few decisions, you automated very few things also. Okay? When you decide that I'm going to have sliders and buttons and so forth, you make some decisions about what the UI is going to look like. It's going to be a button, it's going to be a slider, and so forth. So you can provide more automation, but then you can't do arbitrary graphics. That's what this is called graphics. It should be called arbitrary graphics. And then with the console-based thing, you decided it's going to be all text-based. Okay? So what you see in my class notes is how to build a console-based UI. Okay, with the model interactive technology. And what you have to do in your assignment is build a GUI with the same architecture. Okay, that may or may not be easy. And if it's not easy for you, I'm going to present just at some high level, some conceptual differences between the two kinds of interactors and how do you interactors so that you can make your transition to the GUI interactor easier in your assignment. Okay, so that we'll see next time. Any last minute questions? Okay. Okay. And the abstraction layers can be put in the following, can be shown here. There's windows, okay, where we'll see exactly what a window is, but there's a window abstraction. I kept using the word shared windows, and I was using the windows in a technical way. So you can create just windows, or you can, and so then you have a window-based or graphics interactor, okay? Or you can put some layer above windows, which are special kinds of windows, which we'll call widgets, okay? Text component, button, slider, and so forth. And now the applications you build are either toolkit-based or GUI apps, okay? Or you can say I'm going to put a particular console text component on top of this, okay? And on top of which, and then we have a console-based interactor, okay? So there are 3 levels of abstraction here. And you also see that there's a little, why do you have 3 levels? There's a trade-off you have to often make between automation and flexibility when you design a system. Do you try to support a large range of applications? If you do that, you make very few decisions about the applications. So you're flexible, but because you made very few decisions, you automated very few things also, okay? When you decide that I'm going to have sliders and buttons and so forth, you made some decisions about what the UI is going to look like. It's going to be a button, it's going to be a slider, and so forth. So you can provide more automation, but then you can't do arbitrary graphics. That's what this is called graphics. It should be called arbitrary graphics. And then with the console-based thing, you decided it's going to be all text-based. Okay? So what you see in my class notes is how to build a console-based UI, okay, with the model interactive technology. And what you have to do in your assignment is build a GUI with the same architecture. Okay, that may or may not be easy. And if it's not easy for you, I'm going to present just at some high level, some conceptual differences between the two kinds of interactors and how do you interactors so that you can make your transition to the GUI interactor easier in your assignment. Okay, so that we'll see next time. Any last minute questions? Okay. Okay, so last time we started looking at the distributed aspects in this class. Okay, so far we just looked at how your single user architecture should go, and so that we can later extend it. And now we're really extending it. And when we were looking at single user architecture, we were looking only within one JVM or one process, essentially. Okay, and we were saying what are the objects within this, and how do we decompose our full program into these objects. Now we have a more interesting challenge, that what are the new kinds of objects we have to put in a process so that it can be distributed or collaborative, actually, here in this case, and what are the other processes it has to deal with. Okay, so there's a process architecture and there's an object architecture. So those are the 2 things we're looking at. And of course, once you decide on the processes, you have to figure out what host to put them on. That is a deployment issue. That's not a programming issue. Okay, you might want to put some server on a heavy machine. You might want to put a server on a machine that's available to you, which may not be such a strong machine. So that's something we won't really get into. And in your programs and in the demos I showed you, you'll be running all your processes on one machine. Your program will run on one machine or multiple machines. The way IPC primitives are set up today, it doesn't match. Now, the architecture that you would come up with, both the process architecture and the object architecture, depends on what mechanism you use to put things on the network. Okay? You saw when you built your GUI applications that the GUI library dictated to you what kind of object architecture you would have. If the GUI library supports listeners, then you have to put listeners. Okay? So that's the observer pattern you have to implement.
So our architecture is going to depend on the library. And we're going to begin with, the world of distributed computing and say, okay, we're not going to put things directly on the network. Okay, that's networking. We're going to use some distributed layer. Okay, something that's provided by the operating system, something that's provided by your language, actually, which is built on top of the operating system. And there are many mechanisms to go and put things on the network. There's sockets, there's RMI. Okay, within sockets also there's non-blocking and blocking. So we'll abstract out what this layer does, see how we can use this layer to build collaborative applications. Okay, see what kind of process architecture we come up with. And what we'll then do is we'll say, okay, this is what we did for this particular application. Okay, we'll take our IAM application, see what kind of process architecture we can build. We can create using just a very abstract notion of IPC. And then we'll say, can we generalize this and maybe build a layer on top of inter-process communication that is meant for collaborative applications? Okay, and then what kind of architecture do we have with that? Okay, and in fact, we'll in this course go through a series of these steps where we try to build the most general layer we can build first on top of inter-process communication, and then we'll build narrower layers for certain ranges of applications. Okay. So let's go and see how we can use our IAM application, build our IAM application using IPC. And let's say the user types a message. It has now to go. We're going to run an IAM. We're going to run an IAM program on each user's machine. Okay. In general, this can be asymmetric, but we're going to have a very symmetric situation where every user is running the same program. Okay. Let's start with that. Okay. And so the user 2 goes and enters a message on the console. The message has to go to all the other users. Every user is running an IAM application. So somehow we have to find a path from this computer to other computers. And that's where we use inter-process. So what we'll do is give that user immediate feedback. Okay? That's sort of a principle in collaborative computing. You don't wait for messages to go across the network before you give feedback. Okay? So at least your single user interaction didn't get affected. Okay? And here's the format of inter-process communication, that we go and submit a message to our local inter-process communication layer, whatever that might be. It might be sockets or RMI. In all of these cases, the message you have to go and choose some host somewhere. And on a host, you can have many processes. Okay, so you have to go and say, this process, or maybe actually this service provided by this process. Now, process IDs are ephemeral. They're temporary. I mean, they just come and go, whereas your program is written before that. So we don't go and use process IDs. We go and use some port identification. A port is like a mailbox. Okay, so just as when you have a mailbox outside your house and messages get delivered, or snail mail gets delivered in the post box, on every computer there's a bunch of post boxes. Okay, and when processes come up, they go and say, okay, these are my post boxes. Another process might say, these are my post boxes. And think of these, if you dealt with any kind of web interaction, often these post boxes have IDs or numbers. So port 80 is your web server post box. Okay, so the web server is expected to receive messages from that, and other processes receive messages from other ports. Okay, and these ports may not be IDs; they may be higher level abstractions. But the point is, there's something within a particular host. Okay, so the addressing goes first. You choose host, then you go and choose some port in that host. Okay, so you basically send one message to user one's IAM, okay, by saying which host user one's IAM is on and which port it is listening to. And then you send another message to user 3's IAM, okay? And everybody has now sees the message, okay? That's an abstract version of what happens. You have to use certain APIs to go and actually make this happen, but conceptually that's what's going on. Okay? Question? Lots of questions here. I haven't told you the complete picture. So one question is, how did this particular IAM
know about host 1 and host 3 and the ports, we can agree on, but how does it know about which hosts to send messages to? How did it know that?
Sometime prior to sending this message, they all had to register with each other somehow.
Somehow. So there's many ways possible here. And if you live through the dark ages, as I have, you often just on email say, hey, I want to be in the session, this is my port number, and an email you send to some other person, and you send to everybody who wants to collaborate together on this application, here's my IP address, here's my port number, and then every person goes and tells their IM, okay, these are the port numbers and host. Okay. Have you guys ever used NetMeeting? Have heard of NetMeeting? So one person has. Did you ever use this kind of?
I've heard of it.
You've heard of it. So that was one way to do these things. And in fact, the initial applications were all, this is a static way. Okay? This is hardwired. You know each process when it is coded, or it takes input from the user saying, tell me the host and tell me the port number. Maybe the port numbers we can all agree on. At least tell me the host. So what's a nicer way to do it? We can use email, we can use phone, and the user can input things, or we can automate this process somehow. And Nick suggested that we kind of some kind of registry. You suggested?
I just said register.
Register. So if you're going to register, then you need a registry, right? So that registry will be what kind of entity?
Server.
Another process. And since it is providing a service, okay, that the processes, and what service would the registry provide in terms of operations? There's going to be register, and what's the dual of register? Lookup. Okay. Or basically when you register, you get callbacks maybe, saying so-and-so has registered. Okay. So how did host 2 know about host 1 and host 3? Okay, that was the question. And you could have static, hardwired, dynamic sessions. Okay, I should have an or there. And dynamic sessions means that it's not hardwired. Okay, the user, each user is oblivious of which other users there are. Okay, and processes can get added dynamically, and that's what we'd like to go towards: dynamic session. A session, you can imagine, the English word here means. So when you interact with one application and one user, you have an interaction session with that application, right? Now we have multiple users interacting with some logical application. So they're all in one session, okay? And each user is coupled to the other user, okay? So this registry we'll call a session manager, okay? And as you saw when I was starting up my demo, I not only started Alice, Bob, and Kathy's IMs, which is what these 3 IMs are, but I also before that started a session manager somewhere, okay? So we've put another process in this whole picture, which is a session manager. Okay, who knows where it is? It could be on the first guy who started the session. It could be on a special server we've got for that. We are just looking at the process architecture. Okay? So now our interaction is a little bit more complicated. Before we start sending messages to each other, we have to register. Okay? And how do we, and what do we have here? We still have IPC. Okay, so what we've done is we've taken the regular IPC, whichever our favorite IPC is, we're using it, and that IPC is allowing us to talk to both our peer IMs and the session manager. Okay, we haven't changed the IPC layer at all. Okay, and what we do is, I'm not sure what this animation was. Before we start, we go and say, okay, somehow we know so we have to know about some remote machine. Okay. Now we have to know only about one remote machine, which is the session manager host. Okay? And we tell it, and we have to know its port also. Okay? There may be many processes running on that machine. And we say, okay, I am at host 2, and I am listening on port 2. Okay? That's the port I found on my machine. Okay? There are these static ports that get allocated to well-known services like the session, web server, and they can be these dynamic ports also. So who knows this? We may not have an agreed upon port, so we'll send the port also. Okay. So similarly, machine 1 does the same thing, right? And now how do we do the lookup? So we can poll. Every now and then this process can say who's around, or we can do equivalent interrupts. Okay, so you guys have all probably seen the machine architecture. And interrupt is like having a notification or a callback. So when user 2 registered, there was nobody else in the session, so there's no information returned back. When user 1 registers, user 1 should be told. So what kind of information should we send from the session manager to the processes?
There should be each user could set a callback for what to do when another user joins or leaves.
Right.
Or does something.
Right. So basically, both of these two users should receive some information back. Okay. Somehow, the IAM session manager knows their host and port number, so it can always send that information, and that's burnt into the session manager. So it sends to host 1 on port 1 the fact that there is now another session, another process that's in the session, and its host is H2 and its port is P2. Okay, so this guy gets this, plus host 2 gets to know about host 1. Okay, so they now both know about each other, and when host 3 joins, host 3 gets back now a list saying, okay, in the session are host 1 and host 2 on their ports, and the other guys get a message each saying, okay, I flip between U and H a lot, so this U should become H. I'll try to fix that. So we get back information about the other parties. Okay, so now everybody knows about everybody else. Okay, and now we can indeed have the interaction we had originally, where they are sending messages to each other. Okay? And at this point, the session manager is out of the picture. Once they know about each other, they know about each other's hosts and ports, they can send messages to each other. Okay? So that's your basic dynamic session. Okay, and I say dynamic P2P. Okay, so there was static P2P, now there's dynamic P2P. So I change one adjective from static to dynamic. What can I change P2P from? I can change P2P to what now? So P2 client server meaning, so what would that mean logically? So how would this picture change? How would they be exchanging messages? Through the session manager. Okay, so we'll call that relayed. Okay, dynamic sessions, but they're being relayed through the session manager. Now we know, sorry, again, this particular arrow shouldn't, is animating wrong. So what happens now? You send a message. The message goes to the session manager, okay? And it goes and sends messages to the other people. It knows about them. It has all this information. It's not just a passive registry now. It goes and says, let me just send the message to them too, okay? And it sends a message to them. Okay? Now why? I mean, indirection is great, right? I mean, that's, whenever you have a problem and it's really, you're not finding a good solution to it, there are 2 or 3 things you should try in systems. Okay, what are some general techniques to make things work or work fast in systems that you can think of? That you hear again and again in many courses, you see. Some caching. Okay, and indirection. It's amazing how many problems get solved through indirection. Okay, so we're going to use indirection here. We're using indirection here, but are we really solving a problem? I mean, rather than sending a message directly from, say, Australia to another person in Australia, I'm going from Australia to United States, and to Australia, to United States, and then to China. I'm increasing the latency. I mean, this seems so stupid. But intuitively, you guys saw this alternative. So there's a session manager, use it. Client-server computing, that's what we hear a lot about. Let's create even a more powerful server, not just a passive registry, but something that's forwarding also. So can there be any argument for going through them, to the session manager?
Laziness. You don't want to have to compute. You
You don't want to keep track of. So
Or if we don't want the users to know about the existence of all the other users, if we want to be able to spy on the users by having like a hidden user that only the session manager knows about.
So what you're saying is, let's reduce the awareness in each IM about other IMs.
Yes.
Okay, the message is just going. Who knows who it's going to? See, it's great to ask these questions because you get answers you never thought about. So you say, the information, what we did earlier was, we cached the information that was in the session manager, right? All that information was there in the central person. By having these callbacks, we had that information cached in our local computers, and we used that information to go and send messages directly. Now, we don't have to have that information locally. We just send the message to session manager, whoever it knows about, it sends to, and we may not even know who is around. Okay? So if I'm giving a lecture to, lots of people in the world, it doesn't matter to me who is listening to me. Maybe I shouldn't know also about it. Okay, you guys who work in security, you must know about this need-to-know principle, which says that you should not, or actually in military, that term came around in military actually, that don't provide information that you don't need. Okay, so maybe we never keep locally that information. So I never get to know who actually registered. I just know somebody registered. Okay, and laziness also, that from these callbacks, that I got callbacks from the session manager, I had to create a data structure of everybody in the session. Right? I had to go and figure out there's host 2, port 2, host 1, port 1, at host 3. I have to keep that information so that whenever a message has to be sent, I can address them. Now I don't keep this data structure at home. I don't cache it because caching requires some work, and it's all done in the session manager. Okay, those are two good reasons that I don't have in the slide. I'll try to put if I can remember. Okay, but at least it's there in the recording. Other reasons?
Perhaps if we have like a vast number of users, then we can't really expect the users' machines to handle all the heavy lifting and contacting everybody themselves.
Excellent. Okay. So if this is a little mobile computer of mine, okay, and I'm making a presentation on the beach, okay, to millions of people. Okay. And of course, it's wrong of me to be at the beach when I have 1 million people listening to me. But let's just theoretically say that that's true, or even 20 people. Okay, my little and I've got only so much battery left in my computer. Okay, every time you put data on the network, you guys know when you turn networking on, it drains your battery. Okay, so I use some cycles, and I use some power. So why don't I go and send a message to some central server which is powered on, which goes and sends the messages to the 1 million people or 20 people? Okay? And I might be on a very slow link from my beach to the world. So I send one message on the slow link to this powerful computer, which goes and sends messages on fast links to everybody else who's not at the beach and who's listening to me. Right? So in fact, there are situations where for power reasons, for performance reasons, you want to go through a central relay. Okay? Other reasons? Supposing you're at your home, 2 people at home. You think you guys can really, how many of you have interned at companies? At companies, can you really use this architecture of talking directly to each other? Why not?
I mean, there's all kinds of security measures in place. First of all, your network is
some firewall.
Right. So there's, like, especially with big companies, none of this is going to work to do direct peer-to-peer without a bunch of technology to do that.
So, this is something that I was not familiar with living in an academic environment where, every host is addressable. Okay, but when I spent some time at Microsoft, and they have firewalls. Okay, and the reason why you have firewalls is because you don't want some process on your computer to be listening to messages from other computers, because then you can have a denial of service attack. Okay, the moment you put a little process that is willing to receive messages, which has a host and port number that other people know about, other people can go and inundate you with messages. Okay, so networking is a very tricky issue when you're in a company, and you say, well, if you run a program as a client that fetches information from another process, that's okay. Okay, because you know about the other host and port and you got data back. But if you are a server of some kind, which means that you have a host and port number that people know about, then it's dangerous. Okay? And of course, there's ways to cheat around it because people want collaborative applications with good performance, and they use the HTTP, and they say, well, we'll make exceptions for the HTTP protocol, and on that protocol, there's a way to get data back, and you can have denial of service. So there's a real game people play in companies where they think they're being safe, but because when they're being safe, you can't do certain things. So then you can, in fact, build such collaborative applications where you can have denial of service. Okay? But firewalls causes problems. Okay, so why indirection? Many reasons for using Relate. Consistency, you guys forgot about consistency. That's something you mentioned way off early. Remember, I think Fred was the one. When we were talking of causality, and we were saying that, when you have peer-to-peer communication, you can get into non-causal interaction. Well, if you go through a central server, you'll get causality. Okay? So there's causality, there's security issues, there's performance issues, there's lazy coding issues. Okay, so there are many reasons for having Relate interaction. Okay, so what have we done? We have basically used IPC, okay, as such. And we put a server there. And that server is providing us with some functionality. Okay? And through the server, I'm getting a high-level abstraction. Okay? But my communication mechanism is still IPC. Okay? And my next challenge is, can we build a higher level architecture abstraction that doesn't use IPC? And the key there is that this is something that I built for my IAM application. Okay, so when I teach distributed computing, I just tell people, go build your session manager. Okay, and they get a lot of practice using interprocess communication. Okay, but that session manager is something they build for their particular application. Okay, so we still do IAM applications. Actually, IAM and other kinds of applications, and they build something that is specific to that application. Now, and so I want to do two things. I want to go and come up with a higher level abstraction than IPC, and and the key to doing that is to say, look at this particular process here and say, how much of it was IAM specific? Was there anything IAM specific here?
Just passing messages.
Just keeping a data structure, and based on that data structure was just passing messages when there was relayed communication. Okay. So here's what I want to do. I want to build something higher level that is meant for group communication. Okay. So when you are communicating with a group, you often talk of multicast. See what that really means. And I came up with an IAM specific session manager. I came up with a session manager that I labeled as IAM session manager, but there was really nothing that was IAM specific here. And there were these. This is sort of the protocol between the user processes and the session process that you joined first. You joined by sending a specific kind of message to the session manager, and then you went and sent another kind of message to relay information to the session manager. Okay, so there's two kinds of messages. There are three kinds of messages being sent across a network. One are these join kind of messages, okay, where you say, I exist. Okay. Another kind of message is these callback messages saying, so-and-so exists. Okay. And then there are these messages that you send saying, please go and communicate this information to another process. Okay. So let's just go and look at first these join messages and these join callbacks. Can I build some higher level abstraction that reduces the pain in sending these messages? Okay. So what's the pain? Well, let's look at one pain here. I had to go and send the message, figure out the host session manager. Okay. That's something you can't avoid. I mean, in general, session manager will be at some host that is not fixed. So when you run your application, you have to go and you have to know about the host. Okay. Port. Can I somehow, when I have a generic session manager, can I get rid of this information? The session manager port? When you talk to a web server, do you go and say port 80? You don't. Why? Because that's now a generic service. It's not my IAM session manager that had to go and fight for a port on its machine. Now it is a generic session manager. Maybe it's listening to port number 85. Okay, that's probably taken by somebody else. Okay, but it could be that. Okay, so I don't have to go and provide that maybe. Okay, maybe that can be, and so if I'm not going to provide that, I need to replace IPC with some other layer that's going to fill that port number for me. Okay, so no, I no longer use IPC directly. I use some other library, a higher level abstraction, that knows I'm talking to a session manager, and it goes and says, okay, you're not doing a generic send, you're doing maybe a join. Okay, so it's going to have now a different API. With interprocess communication, you have sends. Now it's going to have a special join call. And in the join call, you will give the host number, host. But maybe the port is something the join call can automatically figure out. Okay. Now I had to go and give my host and my port. Could we somehow avoid sending this information in the join call? Can the join call automatically fill this information?
So the backend, the join call can figure out who sent it from which host and
No, right now the join call is just going to send a message, send some information to the session manager saying, this is my machine's host and this is the port on which it will receive callbacks. Okay. Now can the join call automatically figure these two things out? Can a process figure out its host? Every process can figure out its host. Okay, you can make some call. Okay. So rather than I making the call, my join, this library that I'm going to have, it can figure out my host. And now my process had to figure out some available port, right? The join call itself could do that job. It could go and figure out the next port, and it could go and send the port across. Okay. So let's go and see. I'm going to go from IPC now to a generic session manager. I went from a specific session manager to a generic one. And the question that I just posed to you was, should clients have to know about ports or send its host? And the answer I just gave you was, perhaps no, because now I'm going to have a much cleaner call. I just say join this particular server. Okay, I've got some code here that's doing this. This code resides on my machine, just as my socket layer and my RMI layer resides on my machine. Okay, now I have some layer on top of that resides on my machine that goes and figures out a port, chooses a standard port. Who knows? That's not my headache. Okay, and it sends an appropriate message to the generic session manager now, and not the IAM specific session manager. Okay, so this group communication layer is tied to the protocol defined by some generic session manager. Okay, once I've decided on a generic session manager, I can build a local library like that that's reusable. Okay, questions so far? Okay, so local library at each site. IPC send replaced by group communication join. Okay, and library could fill in port a la web browser and can also register own port and send its host. Okay, just what I said earlier. Okay, So again, like I said, you know, the session manager host, there could be many session manager hosts possible. The library can't figure that out. It's just a passive piece of code that resides there. And somehow you know the end user is supposed to make the decision through the end user's application. Okay? So that information is not automatically computed. So that's one thing you need to know. So as before, the session manager can, so let's now consider the direct alternative, okay, where things are being sent directly, and there are many reasons to send information directly also. So in that case, the session manager, based on this information, can send information to the library about you know, the hosts, other hosts, and ports, okay, which can be used for direct communication. Okay. And so now what I can do is, once we get that information, I can send information directly to my peers. Okay? So my join call was easier. In the direct case, my communication is no easier. Okay? I still have to keep track of hosts and ports if I'm sending messages directly. Okay? Can I make that also easier? So I want direct communication, but I'm lazy. But I have a local library.
The local library could keep track of all the other users and just have a multicast method call.
Exactly. Okay, so we thought that this multicast method is only available when we do relayed. No, as long as we have some code locally that's caching the information, keeping track of all the other users and all the hosts and ports, we can still have direct communication, and we can have our cake and eat it too. Okay, we can have direct communication, and so we need a multicast call, so better communication support. Now what I do is, when the user enters a message, we don't do send messages. We go and first give local feedback as always, and I have a multicast call. I just say, send to everybody else this message. The library knows who everybody else is, and it sends it to one person, it sends it to another person. Okay? So we are making our abstraction higher level. So application code does not have to define any callbacks and maintain information about participants. So there is information cached. It's just not stored. The caching is done automatically for us. Okay. Now I use the word. So application code can be unaware of specific users. It knows there are other users around. It just doesn't know who the other users are. And so we might have all the security guarantees we wanted earlier also, if we trust our library, if we know that somehow the end user can't extract that information from the library. But once it's reached your computer, you can hack it and figure out, you know, what information is received. Okay. Now, I use the word application level multicast. Why that adjective? So you guys see why it's multicast? The same message is going to multiple recipients. Okay, you made one call and multiple messages went. Why is it application level? And what's the opposite of application level?
Library level?
Actually, this was library level. Application level is a misnomer the way we are thinking, because there is this application and then there is this library. So what really happened was that this library did it. Okay, so there should be library level and application level perhaps, but they're both considered application. Who else could multicast?
Physical level?
Physical level. So what would that mean? And this is very interesting. The term is called, yeah.
Protocol or hardware supported multicast.
So the hardware could do it. It'll be just faster. Between my hardware and your hardware, what other hardware is around when we are sending messages to each other? Yeah.
all the routers in between?
Could the routers do some multicasting? Supposing I'm in Australia and I'm sending messages to 5 people or 1 million people in the United States. The router that connects Australia to the United States could have send one message to a router in the United States, and that could go and send 1 million messages. And maybe 20 of us are here. So maybe our site receives only one message, and it forwards to 20 other messages, to 20 other sites within here. And maybe the 20 of us are on one Ethernet, which means we're on a broadcast medium, and every message can be snooped on by every other message. Okay, so just imagine there are 20 computers that are tapping onto the same wire, and they're just saying, oh, is the message for me? I'll take it. If it's not for me, I won't take it. Okay? So that's a broadcast medium. Maybe at the physical level, only one message went across. Okay? So that's network level multicast. That's not what we're doing here. Okay? We're doing application or library level multicast. Okay? So multiple messages are delivered to the network layer, not one message. Okay? And a single message delivered to. So in network level multicast, a single message is delivered to the network layer, which can result in a single message being put on the wire for multiple destinations. Depending on the route the messages take, different things can happen. Okay? So this is multicast. And in this case, we send messages directly to each other. Okay, so when we say to others to our library, are we really saying should it go directly or indirectly? We're just saying to others. The library could send it directly, or it could send it to the session manager. Right? So it could just as well, for the same call, could be processed in 2 different ways. Okay, in this case, relay, and another case, directly. So now that we have this library that somebody else will write, okay, we can just put a lot of functionality in it and say, you know what, library, give me both choices. I don't want to change my code as I go from P2P to relayed mode. Okay, maybe you choose what method to choose, or I will specify at configuration time that I want relayed or I want to do central. If I'm implementing the assignment on causal broadcast, okay, I'll go and set up parameters saying I want direct, so that I can build my timestamps and test them out. If I'm doing operation transformation, where I expect information to go through the central server, I'll just change the parameter to direct. Okay, so library can support both forms of communication. It can choose based on security and performance characteristics, but it can't choose consistency. That's up to you. Okay, and actually I had a student who did a PhD with me who was able to go and select based on performance what kind of multicast network should be built. Okay, so you can have information being multicast to one server, which can multicast to other servers. You can just build a whole tree of multicast, a whole multicast tree, and he would build the multicast tree automatically based on, you know, how powerful your computers were, how fast the messages took, how much time the messages took to go from one computer to another computer. Okay, so you had to basically come up with an analysis and a bunch of equations and then solve those equations for a particular system. Okay, but we're not going to do that in this course. Okay, we're just going to be very simple. So we're going to let the application choose what kind of communication is going to happen. Okay, so our join call now is a little bit more complex. We don't say join as this and just give the host number. We say, I'm joining the session and I want direct communication from my host to everybody else. Okay, and somebody else can join. So each site chooses independently. I'm not sure whether there's much flexibility practically to be gained from this, but that's what I support. And then you can, or you can say, I want to join and I want relayed communication. Okay, so just at join time, which is configuration code basically, you specify the route the messages will take. Your other code doesn't change at all. Okay, Questions? Okay, so we have multicast. Okay, multicast means that one message results in multiple messages being sent ultimately. And so we have multicast or group communication, where we're saying send messages to this group rather than to an individual. Okay, and the specific group that we have here is, the adjective I've used is others. Okay, which means, hey library, you know who I am. You know who everybody else is. From the set of all participants in the session, subtract me and send messages to them, to the resulting set. Any other adjective you can think of besides other? Sorry?
Groups. Group 1 and 2.
So just name some groups. So choose some groups. So Alice and Bob in one group and David and Elizabeth in another group. Can you think of an application that would require that? That's the obvious thing to do. And that's something, that I allow. But can you think of some reason for that?
You want chat room sessions.
So if you have a chat room session, very good. Then can you have subgroups within that? Does it make sense? I've never been to a chat session really.
You support multiple groups.
So there's different sessions for sure.
Yeah.
Okay, there's one session discussing philosophy, another session discussing a video game. Okay, fine. So that you're going to have different sessions. What about within a philosophy session? Might you want to go and communicate with a subset of those people, or think of this physical room here. Okay, so we're all talking to each other, but having taught enough, I have seen side conversations where the person goes and whispers something to their neighbor. Might you want to support something like that in a virtual conversation also? Have you guys seen anything like whisper in any chat room? There is? Okay. And then you can imagine subgroups also. Okay. And what about all? Send the message to me and everybody else. Does that make sense?
I can't think of a situation where I want to do that, but that's not a reason to not implement it.
So yeah, it's interesting, how you design things. I think the argument you just gave is a good one, that you want to think orthogonally. You want to say, here's something like this, and let me go and look at all possibilities and support them. What harm is done through that? And you're smiling. Why?
Well, you always have limited things that you can do, both limits in money or people's time to make things.
So here's a guy who gets paid to do his work. So.
But also, things like software that does everything is almost impossible to use, right? It's really difficult. You have to be a computer scientist.
Yeah.
And you don't want that most of the time. So it's expensive in people's user time.
So somebody had to implement it, and that costs money. And there's a word for it, bloatware, right? A lot of features, and Microsoft is given a very hard time by security guys because they have a lot of features. The trouble is every feature, every API call that you create also creates a security hole. That's yet another call that somebody can use to abuse it. So if we know nobody's going to use it, let's not support it. Okay? So that's the flip argument. So, so as systems people, in systems there's this whole thing about mechanism and policy. And systems guys are very proud of the fact that they focus on flexible mechanisms, saying we can support everything. Okay? And it's the system administrators, the peons, the guys who really can't think, who are going to do the policies. But the fact is the policies are the hard things. That's where the challenge is, because you've got to make choices. So we do want some kind of motivation. So can you think of a motivation for all?
Well, if we're using the session manager style communication and we don't do all, then it seems like we'll get messages out of order, because if you don't send it to the session manager first to make sure that everything's going in the right order, then your message will show up on top of something else potentially.
Yes. So if you want every side to receive all messages in the same order, if you want every side to process all messages in the same order, we were cheating here when we said, oh, when the user inputs a message, the user gets immediate feedback. The moment you say that, you need operation transformation, you need some mechanism to cause consistency. And what if the five of us are all in one room, connected to a fast network? It doesn't cost much. It doesn't take much time to go to another host and come back. I've done some measurements, and it's within 3 or 4 milliseconds to get feedback. And I've done some measurements of how long it takes for the display to update, and that's 20, 30, 50, 100 milliseconds also sometimes. So the display costs dominate over network costs, as long as the network is fast. It's only when the network is 300 milliseconds, from India to the United States, that we have these issues. Okay. Having said that, again, a principle in collaborative computing is that we get immediate local feedback. Okay, but it doesn't have to be, and we can imagine a communication style where we send so the next few slides. Okay, to all. So now I send a message. I don't give feedback to the local user immediately. Okay, I get a message back, and now feedback arrives, and everybody else gets messages back. And now, as long as the group session manager is serializing these messages, everybody is seeing messages in the same order. Okay? And in your assignment, for your regular communication, I say fine. Let messages get out of order. But for your locks, so locks are to prevent inconsistencies. But how do we prevent inconsistencies in locks themselves? It's like who polices the police? And for locks, we are going to use this kind of communication, where everybody will see the locks request in the same order, and the latest guy will get the lock, or the earliest guy will get the lock. Okay? So this to all call will be useful to you later in your assignment when we do locks. Because locks is one way to go and make sure that we don't have concurrency, we don't have conflicts. Okay, so we don't have to worry about messages being out of order, but then the messages about locking have to be in order themselves. Okay, it's one of these bootstrapping problems. Okay, so that's to all. And you guys live in the modern world where you use chat sessions. I live in the academic old world where I actually read papers. That's how I get to learn about things. So have you guys heard about multi-user dungeons? That's a classic system. And where did you learn it? Wait. Are they still around? You can still use them?
Yeah.
Good. So I can continue to be relevant. Okay? And in there you can say, whisper to something. You can say, okay? So everyone in the room hears what you say. So that's to others. You're sending it to everybody else. Okay? You can whisper to somebody. That's to user. Right? Now you can also mutter where, you can, if you want to send a message to everybody but so-and-so, I can imagine having such a call too, but we'll just go and use your call and say, you know what, any other group, you form the group yourself. Okay? So we're going to say 2 users, and we're going to give the list of users and have the message go there. Okay? That's a flexible system. We have motivated it from end user requirements, so people can't complain to us about security holes. By the way, having spent time in Microsoft, I've seen this argument being given again and again by Bill Gates and other people saying, yes, you security guys complain about our features, but our users want the features. And guess what? Our users win. Right? So that's the thing. And so we say, look, our users want this, so we'll put this in the API. Okay? And literally, I took this principle. I did not first have to all in the system, or and then I started implementing locks. And I said, oh, I should add to all. Okay? I thought of it earlier. I said, let me not, firstly, it was just me coding, so I didn't want, I didn't have an army of people coding, and I hadn't got that there in it, and then, the hard way, the bottom-up way, I put it. Okay? Okay, so now what we are doing, we are aware there were hosts, sports so far as entities that we could address. Now we have users also as entities we can address. Okay, that must mean that somehow we have to create that identity. That means when we do a join call, we not only have to know about hosts, we not only have to know about what kind of communication we're going to have, we also have to give some identity that names us. Okay? And in the system that you will use, it's just a string. Anybody can pretend to be Alice. Anybody can pretend to be Bob. Okay? Ultimately, it should be some private key or some credential. Okay? That is a detail that, that's something I don't worry about. So in that, only that respect, and I believe that is the only respect, is the system a toy system. Okay? It'll let you go and create applications easily. I was trying to use Google's API this weekend, and I just couldn't find, firstly, it's hard to find a good documentation. And secondly, I couldn't find a way to just have a collaborative application involving only me. Okay, I tried to go and use my 2 different Google credentials, and still I couldn't make it work. So at least from the point of view of debugging and testing, this security hole is going to be a benefit. Okay? But conceptually, I haven't said what this user should be. In the implementation that I'm going to give you, it's just a string. Logically, this is going to be some credential. Okay? So logical user ID credential rather than physical host given as argument. Okay? So earlier when we registered our host and port numbers. Now I just go and give my username. And when people send messages to me, yes, this is no longer multicast. Okay, this is unicast. I'm sending it to this particular user. But I'm naming the user within a particular session. I don't have to know about host and port numbers. I'm using a logical name rather than a physical name. Okay. So the code is user aware but not host and port aware. Okay. So what's the situation I have right now? I have a generic session manager. Okay. I have a generic library that gives me a lot of functionality right now. Okay. And my call now, my join call has got hosts, users, and the routing mechanism, specification of it. But we haven't figured out how to scope things out. We took our IAM session manager that we ran for our particular application. So every time we were going to come up with a chat session, we were going to run our own server. We replaced that with a generic server. Okay? So the question now becomes, what happens when there are multiple sessions around? And that's the kind of situation you were talking about, where you had a philosophy chat room and a video game chat room. I'm assuming these are somehow contrasting things. Okay? Well, actually, I am with this set of friends, and I have an I am with this set of friends. Okay? Or I have a hangout, and I've got another hangout. Okay? So what I can do is I can say, okay, my one hangout or one session uses this particular server, another one uses this server. Okay? Like that. And what's the alternative?
The alternative could be all of the IAM clients connecting to the same session manager, and session manager handles like what each one wants to see. But that seems unwieldy.
That sounds unwieldy, meaning that seems complex to program?
Yes.
Somebody else is
Sorry?
And
error prone.
Well, every time you do something, you're going to make a mistake. Right? And we as computer scientists want jobs, right? We want things to do. So yeah, good. We want, and So yes, it requires blood, sweat, and tears, but that all came from me, as it turns out. so we can just have one session manager. And it's not just IMs. I mean, this could be IMs, and this could be editing, and this could be IM. Okay, this could be an audio-video conference, and this could be an IM. Okay, so if you remember, our generic session manager is application independent. Okay, so given that this is going to be error-prone, given that we've got somewhat of a bottleneck right now, given that it's unwieldy, why would we? And it is a logical alternative. Okay, is this a practical alternative? Do we really want this? Is there any practical benefits of having multiple sessions within a session manager?
Means you don't have to send out your identification multiple times to multiple session managers.
Okay, so you're saying if I am in two different IM sessions, I will trust only one session manager. I can, if I trust Google, I can just always be sending messages to the Google session manager. I don't have to worry about the Microsoft session manager or some other session manager. That's an argument. Again, think of firewalls also. Where are we running the session manager? Not on our machine. Right? So if you're running it on some other machine, every time you're going to run a process on somebody else's machine, a lot of questions will be asked of you. And typically, so every time you want an IM session, if you're going to go and have to contact some systems guy and say, give me a port number, give me this ability, is going to be an issue. Okay. And so let's look at the arguments. There are fewer servers as a result. Okay, fewer security holes. This code itself perhaps has become more complex. Okay, but at least there are fewer servers. Shared sessions. Okay, because I can just go to a server and figure out, tell me what are the sessions around, video games, philosophy, whatever, and choose to join in a public chat room, in a public session. Okay, so there's more sharing, more abuse possible also, but more sharing. I mean, the flip side of that is sharing. Okay, and then less overhead. You don't have to go and start a server, get a port. It's just there. Okay, so that's what we're going to do. Okay, now this is going to involve changing our library, changing our session manager. Let's see what overhead does it add on the application programmer. So what does the application programmer have to do differently when they're using a session manager with multiple sessions? Now, the application programmer does two kinds of things. The application programmer makes a join call and makes a multicast call. Does the join call become different?
The join call now needs to specify which session.
Which session? Okay. And if the application is only one session, the multicast call, at join time you specify the session, and multicast time you don't have to. Okay. So session members of one IM should not know or be notified about members of other IMs. Okay, so we want some isolation. That's one of the characteristics we want with multiple sessions. And we also want to make sure that messages don't get relayed to the wrong session. Okay, so this is the unwieldy part. This is the complex part, complexity we've added to our session manager. And so now my join call, the join calls made by this session all take session 1 as an argument. The join calls made by this group take another session. Okay, that's the only overhead added on the application program. The system became much more complex. Okay. So join also now requires access control. Previously, we had our own private session manager. If somehow we could, keep his identity hidden from everybody else, we could make sure that other means are used to restrict access to it. We didn't have to worry about the rest of the world. Now we want this shared session directory. We want sessions made by other people who we may not trust completely. That means the ability to join a session should be controlled. So now suddenly the join call is an access controlled call and no longer, maybe earlier also it was access controlled, but by just controlling access to a particular server, we could have access control. Now the server is public, and you want to say, okay, these friends of mine can join this session, and the friends I'm complaining about in this session should not join that session and should be in another session, right? So we want access control. Okay. Now, shouldn't I have a create session call also? I mean, these are not predefined sessions. I just decided to have my own little IAM session right now. Yes, once a session name is given, everybody else can name it. But should I have some kind of create call that lets other people know about? Or can I somehow change my join call to also mean create? And the second alternative seems more complex. So see what would that mean? And why would you do that?
If the call is made and a session doesn't exist, then the session manager
If the session doesn't exist, the session manager creates it. What would be the benefit of doing this? I mean, accidentally, yeah.
The users don't have to coordinate who's going to create the session.
The users do not have to coordinate who's going to create the session. All users can run the same program. Okay? They don't have to run different programs. One user is creating the session, and the other ones are joining. Now, in practical situations where you have invitation-based sessions and one guy creates and invites the others, yeah, we want asymmetry. But in many cases, we don't want asymmetry. The moment I join, I'll show you an application later, where the moment I start my Eclipse environment, I'm connected automatically to all other people who've used, all of my team members who are also using Eclipse at that point, and we can share information about each other's activities. Okay, I'll show you a tool that's not Eclipse, it's Visual Studio, but you can imagine situations where you don't want asymmetry. So, so in asymmetric programs, one user creates and joins, the other users join, and there are race conditions possible. Okay. Now what we have is a single symmetric program. Whoever's join reaches first, that join becomes the create call, and everybody else just gets the existing session members. Okay. So that's our semantics. Okay. Questions? Okay, this is the tool I was talking about. Okay, so here's a visual, and this is something I worked on at Microsoft when I was there. So this is the Visual Studio environment, and it's a regular Visual Studio environment. You can go and code stuff here. So this is your private space, but because it's collaborative, because I was involved in the project, there's all this other stuff that's meant all for collaboration. Okay, so if you think that your Eclipse or Visual Studio environment doesn't have enough space to do your own private coding, this exacerbates that problem, okay? Because you have all this shared stuff, okay? And what's going on there? Well, I can start a text chat with my team members. I can do a code share with them and inspect some code collaboratively. I can do an audio video session with them, okay? And stuff like this exists in Eclipse also. There was a system called Jazz that also did similar things, and then Rational took that over. In your company, do you guys use something that's collaborative like this?
I mean, we use Google Hangouts.
But nothing that's part of the environment.
No.
Would you use it?
No, I don't think so.
You don't think so? Well, we did user studies, we did programmer studies, and they all, once they used it, said they liked it. Okay. There's actually a group of my Visual Studio group in this area, in the RTP area, that's doing team Visual Studio. And I don't know whether this is going to become part of their product or not. Okay. Anyway, assuming this is a good thing to do. Okay. Why do you think you won't use it?
I think that everyone, I think that at my particular company, everyone kind of has their own way of working.
But don't you want to sometimes do code inspection, for instance, and go and look at code together?
Yeah, a lot of times we'll just do that in like the GitHub interface, like when we're doing code review and things like that.
So how do you share the code? How do you know? As I browse through the code, how do you see the browsing actions? Do you see them? You don't.
Well, if we wanted to do it that tightly coupled, we would do it in like with a shared screen.
Shared screen.
And then like one person drives it.
Right.
If you wanted, you could just switch over. That's how we do it. This may be more efficient than that. We just haven't found any.
Yeah, and we built this thing to avoid, our driving problem was conflicts. We wanted, as soon as the conflict arose, we wanted the people to go and resolve the conflict. So this was meant to reduce, in GitHub, it is sometimes too late. And in companies, people fight with each other to be the first one to commit. So that's the conflict resolution is somebody else's headache. And this was meant to also tell you that, hey, as soon as I enter a method, I start editing a method, and you edit a method, and these two methods have got an indirect dependency or a direct dependency between them. They're the same method, or one calls the other. A little message comes in. The user sees the message and saying, "Hey, you guys might want to go and talk about it." Anyway, so I'll put a reference to this paper in case you guys are interested in looking at it. But assuming this is good, and let me just expand this window a little bit. So here's an audio-video conversation. Here's a chat session, and here's and we are both looking at our code, each other's code, and resolving the conflict. Okay. Are these 3 different sessions, or are they one session? One session with different components. So when I go and send a message in my IM tool, my code sharing tool better not get that message, right? So when I do my multicast calls, I better be aware of these components. But why are they part of one session then? That's intuitively, that's what you think, right? They're all being used to do one task. If there was access control was at a higher level. If I can do an IM session, I can also do an audio-video session with you. I've joined the super session. That's where the access control was done. And maybe when one of us, the team members, joins the IM session, I should know about it, so that I may join it or I may not join it. So in that sense, they are being united. Okay? So we want an abstraction that reflects this. Okay? And so our text, chat, code share, and audio-video, our text, chat, code share, and audio-video separate sessions, or same session. And there are different application subsessions in the same overall session. And no access control required to join applications once you're in the session. And each user knows about users of each application. Okay? So I have to, when you have scarce screen resources, you sort of use up the whole thing, and I can see people in the back trying to see this. I guess we should go and move the the dustbin. Okay. So what's our abstraction? Our abstraction is more complicated. Originally, our abstraction seemed to have sessions, and within sessions you had processes. Alice's IM process, and so forth. Now what you have is a session in which users join without regard to their applications. Okay, users join, not their processes don't join. A user joins. Okay, and then you have certain applications that are joining. So you have the IM, or you have processes joining like IM and editor, and users then go and join this particular session also. Okay, so my Alice's IM session and Bob's IM session client and Kathy's IM client have all joined the logical IM session. Okay. Similarly, Bob's editor client and Kathy's editor client have joined the editor session. Okay. And then Alice, Bob, and client and Kathy, regardless of the clients they're using, are also part of the session. Okay, so users are part of the session and clients are part of the session. Okay, and also application, and there are subsessions that name the applications. Each client has joined a particular subsession, and that subsession is named by some application name, some logical name. Okay, so rather than just having sessions and clients, we have sessions, clients, applications, or subsessions. Okay, and we have just users directly also. Okay. So users in session can interact with any application in session. Access control done when user joins, and users notified of all applications added to session, and all users interacting with the application. So we do need to keep these subsessions separate, okay, for multicast purposes. So let's go and look at what this really means. Now my join call takes not only the session name, which is the overall session name, not only my name, but also an application name or subsession name. Okay, this could be, you could have IM1, IM2 also if you want to. Okay, but typically you're going to have sessions of different types in an overall session. So can you guys go and now give me the meaning of what this join? Okay, I guess we are running out of time. So what we'll do next time is revisit this and try to figure out what this join call really means now in this complicated world. Okay? Okay. Questions? Okay. So we were looking at the composition of sessions. So we saw last time that a session manager may have multiple sessions, and these sessions could be totally independent of each other. And then we saw an example where you sort of had multiple sessions, but they were all part of a larger session. Okay. So the two alternatives are having flat sessions and having non-flat or hierarchical sessions. So in flat sessions, the idea is that in each session you have a bunch of users. Okay? And actually they're not users, they're processes running on behalf of users, and these processes say that I am representing Alice, I'm representing Bob in this session, and any callbacks come to me. Okay? And when that process makes this call, it says, look, of course it finds a session manager. It then goes in, identifies a session, identifies the name of the user or credential of the user, and of course we saw whether it tells the session manager whether it should relay or not relay. Okay? So some process running on behalf of Kathy joins a session, and the session manager is oblivious of application implemented by process. It doesn't know whether it's implementing an IM or editor. It just knows there's some process. Okay? So the side effect of this particular call is to add Kathy to the session. That's your flat session. Okay? In our hierarchical session, I motivated this using this tool that I helped build at Microsoft, but you have things like this in a lot of conferencing systems. Okay? Google Hangout has apparently an ability to add applications to a Hangout. If you've used Skype, I've not used Skype for collaborative computing, but I assume it has these capabilities. I've used live meeting in WebEx. These are. Have you got anybody heard of live meeting in WebEx? Okay, you don't work in industry. Our industry rep is out of town today. These are industrial tools, and you pay by the second or by the minute for collaboration. So, all these tools that you guys use for free, you assume things should be free. You kind of get what you pay for in most free applications. So this stuff is really robust. Okay, this is meant for conferencing. Okay, so all of them have these multiple in them. So now our picture becomes much more complicated. Now my session has, as before, users. Okay, so the session manager knows that in this session are these users. Plus it knows that there are applications in this session. Okay, there's the IM application and the editor application. And it also knows which of the set of users in the session, which subsets of these users are using each application. So it knows that Alice and Bob are using IM and Bob is the only one using editor. Okay, and that's important because if it's relaying information, it has to relay information only to the users of a subsession. Okay, so if an IM application generates some data, it should only be sent to all the other IM users, not to the editor. Okay, so that's the reason it has to have this information. So now our call becomes more complicated. It has an extra argument, which is this IM, and what it does is it makes Kathy join the overall session, right? And what else would it do? Adds Kathy to IM. Okay? And if I go in, if now this call is made, Kathy is already in the session, so all it does is add Kathy to editor. Okay? And does it make sense to join session without joining any subsession? I mean, in this call, I joined the session as an IM user. In this, I've joined as a editor user. Does it make sense to join as just a user? And what would that mean? What benefit would I get from just joining as a user? Fred?
Maybe you can get your foot in the door and see which subsessions have people in them.
You get your foot in the door. You get all the callbacks saying, oh, the editor application just got added. And these two are joining the editor. Okay, now I'll also join the editor. Okay? So David can just join without any application and just say, I guess at this point, this particular parameter also doesn't make much sense. Okay? But certainly this parameter is saying no application. So just join as David. And David's process cannot send or receive messages, okay, because there is no application to send the messages to, and simply listens to session callbacks, okay, which can inform its users of session activity that this user has joined, this application has been created, and this particular process that made this call can also make David join a session. Okay, it can invoke another program, invoke another process that actually goes and joins a particular subsession, and I'll show you an example a little later. Concretely how that's done. Okay? So our session join semantics are the following. Now we have this extra call that is the application, and it says if session not created, create it. Okay, so it's got this argument, session argument. We saw this one before. If session doesn't exist, create it. If user not in session, add the user. Right? If application not in session, add it. And finally, add user to application subsession. Okay, assuming the application is non-null. If the application is null, then of course these two steps are not taken. Okay. So that's our last version of our join call. I showed you many versions of join calls. This is the most elaborate and the one that one we look at. Okay. Okay. So I've told you about the join call. I've told you about the join. Did I tell you about the join callback? Okay, so I might or might not have. Let's go through this again, revise it if I have already told you. So this is how you get to know when somebody joins. Okay, so you get to know which session, which user, which application. You also get to know whether it's a new session or a new application. Okay, this is something that the session manager can keep track of. So why not go and provide this information with the client so that they don't have to determine it. Okay. So that's my callback for the join call. And then when you send a message, you similarly need a callback, right? And what would the arguments of the callback be, of this callback be? So you're sending a data object called message, and the callback should provide you with what kind of information? It should, yeah.
A message to call that a callback method that implements those parameters.
So it has the message. Anything else?
Maybe we should tell you that the other users involved receive your message.
Okay, so there's a callback. This is very interesting. When this guy sends a message, the callback has to be invoked. When this join call was made, okay, let's go back to join call. This join method was invoked in what processes? In the caller? In the other guys? Both?
Yes, both.
Maybe the caller, just in case, if you're using some network primitive that is not reliable, then you might want to get an ACK back. Okay? As it turns out, it is invoked in the invoker also to tell you what other users are already in the session. Okay, so it gives you that information, and it's certainly invoked in the other guys. Okay. Now, when I go and send this message to others, the callback should be invoked in the sender, others, both. So others, should it be invoked? Should something be invoked in other processes? Okay, they have to receive the message. Should we invoke back in the caller? What do you guys think? Assuming that the underlying system is reliable. You might want to build some kind of acknowledgement. It's that everybody's used. These are the ones that have actually received it, and it becomes more complicated. And in the system, I'll show you. That's something you have to build at the application. Okay, and in the applications you'll build, you'll see that you really don't need that. Okay, so now the this callback is invoked in the other processes, and the other processes will of course get to know what the message is. Anything else you might want to send to the other other processes? Think awareness. Time when the message was okay. Time might be important. Anything else even more important than time?
Maybe usage.
Sorry. But it's that's implied. You'll only get messages for your application subsession.
preparing to send a message?
Uh,
Like in an IM client, they can say like this person is typing.
so that would be just another kind of message.
Yeah, okay.
Do you want to know the person who made the made the change, the user who sent the original message? In a lot of applications, you need that. Okay, so when people talk of transparent remote procedure calls, where you don't know, which host invoked the procedure call, it becomes tricky to build certain kinds of applications. Okay, so I've seen special procedure call mechanisms when I was at Microsoft where they actually would add an extra parameter that says this is the user who made the change. This is the host that it came from. So this will be a received callback. It'll tell you which user made the change and the message. Again, you can just ignore that user if you want. If you're going to always ignore, then this is not a useful thing. But this is in practice has been found to be useful. Okay, so I've told you a lot. I've told you how the join call works. I've told you about these callbacks. Is there anything else I need to tell you before I, finish the session? Finish this topic? No pun intended. Are there any semantics that are left unspecified so far? Look at the title of the slide.
Synchronization.
So, what does that mean?
We have not specified in what order. We've not specified whether or not people are going to have a consistent view of events. We have not specified we have not specified whether any of these thread methods are synchronized.
So we haven't specified, when you think of synchronize, the word synchronize is used so much. We talk of synchronous collaboration, okay? And the demos I've showed you and the stuff you'll build is called synchronous collaboration, as opposed to email, which is considered asynchronous. Now, if you use email often, it is. So what does synchronous mean? Maybe it means real time. And if you say that's real time, then all the real time researchers, start saying, no, that's not real time. There's no deadline guarantee. So, and so what term do you use? What is then we use the word synchronous for synchronized methods among threads. So when you have multiple threads, you're saying whether the threads, when they execute some shared method, whether that's synchronized or not, whether it holds a lock or not to the object. So that the word synchronized is used there. So the word synchronous is ambiguous here, but I certainly haven't said anything that could help you determine some consistency issues, okay, which is what Nick was saying originally. And I haven't said whether each of these operations, okay, so I'm going to use the word synchronous in a way perhaps that you haven't seen before, that every operation can be considered synchronous or not synchronous. And this is not the same as synchronized in threads. Okay, it has nothing to do with threads. It has nothing to do with implementation underneath. You could be using semaphores for synchronization underneath to make sure that shared memory constraints are met. So can you guys think of some other meaning other than synchronized method, whether the stuff goes in quasi or real time? By the way, Microsoft decided to go from real time to live. They found that word to be less ambiguous, perhaps, or less overloaded. So that's why there's live meeting, they use the adjective for many things, right? Live messages. So when you invoke a file operation, okay, write or read, people often talk of synchronous I/O or asynchronous I/O. What might that mean? So let's just go to another context and just think there's one process, one thread, it decides to go and write to a file. And you can say whether the write is synchronous or not synchronous. What might synchronous mean in that case and asynchronous mean? So synchronous, asynchronous always involves two parties. Yeah.
So a synchronous write will block until all other writes have completed, and then it will perform the write. And so when a synchronous write returns, you know that the system has been written to. An asynchronous write would probably dispatch something to a queue, and then the thread continues processing.
Exactly. Okay. So we can generalize this and say there is some operation involving two parties. Okay, where one party can work independent of the other party. And in the example of write, one party was the CPU, and the other party was the disk. Okay, and you're saying that the CPU waits till the disk has written and then returns back. So there is some consistency guarantee. Okay, this has to do with consistency. That the party invoking this write knows at the end of the write that this operation completed. Okay, and so the operations could be write to others, whatever. And in synchronous, operation invoker waits until the operation finishes. Asynchronous, operation invoker does not wait until completion. Okay, so synchronous implies so then if you really want to know about completion, some other method has to be found to determine that. It may be an interrupt, which is actually a form of callback. Okay, so in general, there'll be a callback of some kind. Okay, so clearly, synchronous implies blocking. Does blocking imply synchronous? Are the words blocking and synchronous synonymous? So you order something at a restaurant. Synchronous is you block till you get your meal back. Could you block and yet not get your meal back? You could block till a time, you could block at the gate. So there could be blocking, but you haven't finished your operation. Okay, so you can block until the time that when the operation completes, and that's synchronous. If you block for a smaller period of time, then it would be just blocking and not synchronous. Okay, so and why would you ever block for some other reason? I mean, think of again write. I can block till the write completes, till the data have been written to the disk, or I could block until the data goes from your user space to the disk. Does it go to somewhere else before that?
Copy to some memory location?
That the operating system has, the kernel space. Okay, you say, okay, I trust the kernel. So I'm blocking till the kernel has it, and it's possible that the kernel buffers are full, so I'll block till there is some kernel buffer that's available, and then I'll unblock at that point. Okay? I know at that point that it'll reach. I trust the kernel. Okay? So blocking operation invoker in waits, unblocking possibly before, until, or after operation completion. Okay, so blocking doesn't imply synchronous. Synchronous is always blocking. Blocking is not always synchronous. Okay, so now that we understand synchronous versus asynchronous in this context, I mean, like I said, these two terms are used in many contexts. What should our calls be, synchronous or asynchronous? And what does it really mean? So we've got, okay, so before we do that, let's go and figure out what synchronous would mean. So what would it mean for a callback to be synchronous? So the joined call that is invoked by the session manager, what would it mean for that to be synchronous? When does the operation really complete?
The operation completes once everyone who has received the joint notification has completed their callback. So
the operation completes when the callback at the other side completes.
Yes.
Okay, so when it finishes execution at the other side. So this guy, it doesn't just queue the callback, it just waits till that callback is invoked. Okay? And when does this call finish? So supposing I make the join call. If this join call was going to be synchronous, it will block until
well, if the other side has no way of telling the session manager that it's finished its callback, then we're going to be blocking forever.
we assume that underneath we can send acts.
Okay.
Yeah.
Okay.
We can send acknowledgements to scroll. That's how this stuff is implemented.
Okay. Then we could be waiting for a while.
So, so exactly, when does join exactly finish semantically? If I'm going to build these acts, how will I implement these acts so that, so when does a join call really finish? At what time? Till the server executes it? When the server executes it, or maybe even later? I mean, there's some design issues here, perhaps. So one semantics is when, the server executes it, when you are added to the session. Is there a stronger semantics possible also?
So the other users are aware.
So when the callbacks also finish?
Yeah.
That's the strongest one. That everybody, I know when the join call has been executed, that everybody else knows that I have joined. Okay? So when the call and any associated callbacks finish. So now you know what synchronous, asynchronous are. Now, supposing you are designing the system, what do you want, synchronous or asynchronous? And what are the trade-offs? I mean, it's really not, it's always, and why? So what are the trade-offs? What's the benefit of asynchronous?
With asynchronous, our threads don't have to wait on the other threads to finish the execution of the callbacks.
So there's more concurrency.
Yes.
There's less waiting. Okay. So maybe to the user, the interaction is faster. And with synchronous, there's more guarantees. Right. So that's a trade-off. And what might you choose? So you would choose performance, okay, and build maybe other kinds of mechanisms to do consistency. Okay, that's what operation transformation was about. We saw it just let things go and said, okay, if something really bad happens, we'll fix it later. Okay, so so that's what in synchronous call. So let's talk about the call. So when you make a synchronous call, your local response is affected, right? Because the user wants to enter data, and the user enters some message, and your process gives you feedback, sends a message to the server, which sends it to the other clients, and you wait till everything finishes, and then you process the next input. Okay? So with synchronous calls, if the latency is high, then your local response gets affected. Now, there's local response. What other response could there be? Remote response, what does that mean? So in a collaborative system, you want to care about your response. Okay, you want real-time response. Okay, what other response is there? So when I type my input, I want to make sure that the output I receive is, not more than a certain amount of time after I input. What else do we want to guarantee? It's collaborative. Do we want any guarantees for the other user? We want to make sure that the other user's response also is not, it shouldn't be a day after I entered. Right? So that's feedback and feed through. So feedback is local response, feed through is remote response. So if my calls are synchronous, my local response gets bad. If my callbacks are synchronous, then my remote response gets affected. Okay, because the callback is when you get data from the remote site. So if your callbacks are going slowly, then your remote response gets affected. Okay, and you can make trade-offs and say, okay, I'm fine with my local response being good, but the remote response can be bad, and so you can make these choices. So the system I'm describing is all asynchronous. Is designed to be asynchronous. But let's go and talk a little bit about the trade-offs. So we are trying to figure out how to design multicast, and I'm giving you an implementation. And I'm also giving you some choices. Okay, so I'll go and give you an implementation at some point, but I'm also giving you the design space so you can see the trade-offs. Okay, so some other system may have actually synchronous operations. So how much control do I have here once I choose something here? Okay, so at this point, I'm supporting two others. This layer supports two specific hosts. If my primitives here are synchronous, can I make something asynchronous here? And if the primitives here are asynchronous, can I make something synchronous here? So let's answer the first question. Supposing my underlying layer is sockets, which is asynchronous. Okay, can I build a synchronous layer on top by
just synchronizing the methods, or we can make the layer on top synchronous by just controlling when we call the underlying methods.
When we call the underlying methods, and then to do that, we'll have to exactly. And what will determine when we call? What kind of what extra stuff do we have to do? So how does the layer know when to call a method? So is there any communication that goes around? Extra communication that has to go around in the network? Sorry. So we have to have ACKs. Okay. So this happens all the time. So if lower layer is asynchronous, can we make higher level synchronous? And yes, explicit ACKs. Okay, now TCP is not synchronous, but at least it has ACKs, so there is a way of doing acknowledgements, and we can do that at a higher layer, and we can use those acknowledgements to determine when we invoke the next method. Okay, so that's something we can always do. Okay, and that's why many people argue that the lower layers should be asynchronous, so that higher layers can be either asynchronous or synchronous. What about the other way around? If lower layer is synchronous, can we make higher layer asynchronous? Okay. At first glance, maybe the answer is no, which is what you're saying. Think a little harder. My underlying operation is RMI. Okay, I'm using RMI, which is blocking and synchronous. I'm building two others on top. Okay, and I don't want it to be synchronous, asynchronous also. So can I do some tricks? And I'm in Java. Let's say I'm in Java. Yeah.
I think that would depend on how the underlying synchronous process works. And so if it's synchronous and we're using Java, we assume it's using like Java's synchronous locks.
See, locks are within the same process. So to help threads coordinate in a process. Now we're talking of coordination among threads in different processes. And when that happens, the synchronized methods don't help us.
Okay, so I guess the question is, or what I would like to understand is how this lower level layer manages its synchronicity?
Synchronousness? I don't know. Synchronization?
Synchronization.
Yeah.
I would like to know how the lower level layer achieves.
Well, we just saw that, right? The lowest level layer is asynchronous, and this layer here, which is built on top of the very lowest layer, just uses ACKs. Okay? And yes, it'll have to go and use some blocking semantics in the operating system. Okay, which could be synchronized methods to actually block a process. It could be semaphores, it could be anything. In a really bad system, it could be polling. But yes, there has to be a way within that process to block things, and the unblocking is done based on when ACKs come. Okay, that's how we do the top one. Okay. Now the question is, how do we do this? That the underlying layer is asynchronous, but we want to give the user who's making the two others call the illusion that we are actually using asynchronous communication. And think Java.
We can use more threads.
You can use threads. Okay. And how would we use threads then? I mean, let's just talk. So, yes, with separate threads. Okay. So there is one thread that will actually go and make the request to send the message, and there'll be some other other thread or some set of threads that will actually make the synchronous call. Okay. So here's a requesting thread. Here's a sending thread. Requesting thread passes message to sending thread and does not block. Okay? And so the sending thread invokes a synchronous operation. Okay? And somehow data go from one thread to another thread. Okay? Now, how many sending threads are there going to be? And how many requesting threads can there be? So you're designing the multicast layer. Okay. How many requesting threads can you imagine? Is there any constraint you can place? There's at least one. But who creates the requesting thread? The multicast layer or the application? Application creates it. So who knows whether it's the main thread, it's an AWT thread, it's some other thread. Who creates a sending thread? It's the system. Okay? Because the system is giving the illusion. Okay? So the number of requesting threads could be any number. The number of sending threads, what do you guys think? Before we go into that, so when you have this situation where there can be multiple requesting threads and one or more sending threads, this situation is an example of some classical problem that you might have seen before. And what is that? How many of you have done operating systems? One person. Two.
Taken the operating systems course?
Yeah,
or-
yeah,
okay.
yeah. So is there a classical problem that you've seen in operating systems of which this is an instance? Deadlock is okay, I didn't mean problem as in real problem. I meant a class of applications. Yeah, deadlock is starvation of problems in concurrency. But, sorry? Good consumer producer problem. Okay, and so this is a producer, consumer, and what is this? Sorry? A product. How do the producer and consumer problems? There's another entity that you name also. How many such messages can there be there at one time? Is there only one message shared, or there can be more than one message? Pending. How many pending messages can there be? At least one, zero, many.
There can be a buffer size.
Okay, so isn't there something called a bounded buffer that you might have heard of? Okay. So what if two threads work at different rates, which is what we expect here? Okay. What if more than one pending message? So, you have to think of a classical problem, and that classical problem is the producer-consumer problem, and in that there's a bunch of producers, a bunch of consumers, and they coordinate through a bounded buffer. Okay? So this is a bounded buffer, these are the producers, these are the consumers, and now the question is how many producers and consumers? Okay? Producers we can't control. So the question is how many consumers should we have? And at least one. Only one or more than one? So now you see why design of collaborative and distributed systems is tricky. These are all decisions you have to make. So if we have more than one, we'll have concurrency. That means multiple messages could be pending at one time. Okay, so multiple messages could be sent on the line from this particular application. If you have only one, then there's only one queue of messages going out. So what do you want? So,
There should be at least one consumer.
yeah, there should be, otherwise no work will happen. The messages got added in the bounded buffer in some order. Do you want to put any constraint on the order in which they go out?
It seems if you use multiple sending threads, you'll have an issue with the order of things get sent.
And then, and you're saying that you don't want the order to be changed.
Right. So maybe you can attach like a timestamp to each item. Each
Okay.
message.
Okay. So you can attach a timestamp to each message, and that's exactly what TCP does. TCP adds a sequence number, and if messages reach out of order, it rearranges. But its order is determined by the order in which it's given the messages. So we'll have to duplicate the work of TCP/IP to go and maintain that order. Okay? And if we really want the order, we might as well go and send messages out in that order. Right? So here's the danger. So how many consumers? There are consistency constraints. So we have to think not only of latency, we have to think of consistency also. And so here's the situation. Number of producers application specific and cannot be controlled. Okay? And this is the problem that can occur with multiple consumers. So a message is consumed by one thread. Another message is consumed by the other thread. Okay? So this message is consumed by this producer before this message is consumed by this producer. Okay, that's the bounded buffer semantics. But now because you have multiple threads, they can get swapped out. You know, this sending thread after it consumes it can get swapped out. Okay? So what might happen is that message 2 goes out before message 1 goes out, if you have multiple threads. Okay? So greater than number of consumers, greater than one consumer can result in message reordering, which is something we don't want. Okay? So, and why is ordering important? We saw that the reason for to all was to make sure that everybody sees messages in the same order. Okay, and that was the easiest way for us to get consistency. That's not the method we will use. We'll use it only for locks. We won't use it for other actions, okay, because our interaction time gets bad. But even when we go and use 2 others, we are still relying on the central guy sending messages in the same in a causal order. Okay. Of course, when we do peer-to-peer, then we have to do extra work to maintain causality. But we do want to allow the to-all method to provide us complete consistency. So we want that kind of interaction. So ordering is important. And only messages within an application subsession need to be ordered. Okay, so we don't need to order messages, the editor messages with respect to the IM messages. Okay, so we're going to have how many consumers? So we're going to have one sending thread per application subsession. Okay, at both session server and clients. So a client could conceivably be part of both IM and editor. So we'll have one thread for each. And the server certainly has multiple sessions, and within each session it might have multiple subsessions. The server also has multiple threads. If you really want concurrency, because the server could be running on a multiprocessor system, so we really get throughput by having multiple threads. Okay. So threading, by the way, concurrency issues are a big deal in distributed systems. Okay? And that's why when I said prerequisite, I said you guys should all know threads through some means, either through operating systems or through some other means. Okay. So the multicast layer hides this from the. Okay. So let's just see, have we really solved our problems of synchronous layer? So what happens now is that when a process makes a call that says send the message, that process doesn't block. Okay? So my local latency, my response time is good. What about my feed-through time? Have I really fixed that problem through this cheating, by having this extra, I don't know if I should call it cheating or not, but by having this one thread that works asynchronously from the requesting thread, have I really reduced the problem of feed-through time? So feed-through time is the time it takes from my input to generate a response on your computer.
We improve feed-through time in the case when we have multiple messages to send to multiple other users.
Multiple other users also?
So if before I had to send a message to you, and if I had to send a message to everyone in this room, if it was all synchronous, whoever was last to receive the message is going to be waiting a long time. If it's asynchronous, then we're going to have a shorter feed-through.
Right. So we could, in fact, if the messages are going to, so that's a good point. If the messages are going, we need one sending thread per application subsession, okay? And if we are doing peer-to-peer computing, per user, okay? So what Nick is hinting is that we can have separate threads for separate users, okay? And if that is the case, then we've solved the problem that the last user is not waiting a long time, right, for our message. So now think of a sequence of messages I'm sending. Okay, so actually I should really qualify that. I was assuming here that messages are going through the server when I said one application subsession. It's actually per application subsession per user. You have a separate thread. Okay, so there's no need for all users to share one thread. Okay, what about two messages going in succession to the same user?
Then there's, if anything, our feed-through is worse because we've incurred this overhead of managing these threads.
So if anything, it's worse because we have this overhead of threads and we are not gaining anything because this thread is sending messages in order and waiting for the first message to be delivered before sending the next message. Okay, so here's sort of a picture, I think. So requesting thread does not block, so feedback does not involve round-trip delay. Message to server and other clients separated by round-trip delays. Okay, so here's the situation. Here's message 1 generated by input 1. There's no blocking. So message 2 gets generated immediately afterwards because there's no blocking. But message 1 has to reach at the other end. An ACK has to be generated. Message 2 has to reach. Message 1 has to reach at another end. An ACK has to be delivered. Has to reach, and then this guy unblocks, and the next message is sent. Okay. So for each user, an ACK has to be sent before a subsequent message is sent to that user. Okay. So that is now an issue. Okay. If you're going through the relayer, if you're going directly, then we don't have to wait for all of the ACKs to come back. We can wait for each user separately. But here we have to wait for all ACKs to come back from the users before we send the next message. Okay. How bad is this in practice? In theory, that sounds pretty bad. So so I told you guys that when a message from India to here takes at least 300 milliseconds, I've noticed. I've never seen anything lower than that. A message from here to California, or a message from here to, let's just say, California, to google.com.
Depends on how fast you send consecutive messages, but in terms of typing.
Yeah, I'm just saying, how long do you think? We do a ping to google.com. Anybody want to do a ping to google.com and see what the time is? So the fastest inter-process communication people have ever built for local area network is like 2 milliseconds or so. Some people have gone under it by millisecond also. But in general, it'll take about 20, I assume. What did you find, Nick? It's still coming back?
Still trying to bring up my command prompt.
Okay.
No, I clicked the wrong button. It's open to text editor.
Okay.
There we go.
Sorry?
90 milliseconds.
90 milliseconds. Okay. So in interactive applications, 180 milliseconds, is that significant or not significant? No?
I think it can.
Sorry?
There would be some that depends on how much the user wants.
So you guys have any idea how much the user can even perceive? When do they, so when can they tell and what can they tolerate? So from video conferencing, what can we perceive? If the response comes lower than a certain, faster than a certain threshold, the users can't see. You can't even tell. And that threshold is how many frames per second? You guys might have heard in video.
24?
About, numbers vary. 30 is the classical number. 10 also is some people say 10. Okay, so 30 milliseconds, lower than that, people can't notice. So this is certainly higher than that. 180 milliseconds more than 30 milliseconds. Okay, tolerable response. So when you're supposing you're not doing a video, you're just sort of interacting with an application, and if it responds, these events are independent. When do you start noticing the response? It's not 30, it's higher than that. So people say it's maybe 100 milliseconds. Okay, some people say it's 50 milliseconds. So if you notice, when in operating systems, the quantum time is the time that you can hold the CPU, a thread can hold the CPU before it gets scheduled out, is about 100 milliseconds. Because that is what people start noticing. So if you want to create interactive applications, no matter how fast the processor is, the operating system still provides you with 100 milliseconds as the quantum time. Okay, so that's what people can notice. So now let's go and look at our applications. How bad is this in practice? So round trip times, I think I picked a good number. I said 100 to 2,000 milliseconds. Okay, I've never seen anything. I've seen sometimes 30 milliseconds actually, or 40 milliseconds. Time between telepointer movements. So when you move a telepointer, and I've noticed it's about 10 milliseconds is the time between telepointer movements. And if you want the telepointer movement to be registered smoothly at the other end, the event should be within 30 milliseconds of each other. Okay, so by the way, the corollary of this is that at the sending side, don't send telepointer movements that occur at intervals less than 30 milliseconds. It's just not going to be noticed, and you can really save on time. Okay, so this is really bad if you're doing telepointers. Okay, and I've really tried it. I've tried telepointers across a network with delays, and it becomes really bad. So there is a cost of making the underlying layer synchronous. Okay, and that's a cost in the system I'll give you. That's a cost you bear in that system. Okay. Okay, so we've talked about the sending threads. Okay, there is a requesting thread that requests a message that's created by the application. Then there's an actual sending thread that the system creates that sends the message per user, per application subsession. Okay, for peer-to-peer, and just per application subsession for relayed. What about the incoming messages? Which threads are actually invoking the callbacks? Which threads receive these messages that come in from the network? User threads, system threads?
It would initially be threads controlled by the operating system, right? Over a network.
Yep, and it'll be operating system, and that'll give it to the maybe RMI layer, and then the RMI layer will give it to the multicast layer. Okay, it's not your thread basically. The callbacks get invoked in some threads created by some other foreign entity, and it was not your application threads. Okay, so ultimately, then you have to decide. And what happens with RMI is that if you have multiple RMI calls from different sites, they get serviced by different threads. Okay. Or in fact, even actually, I think RMI doesn't even allow multiple RMI. Yeah, it doesn't allow multiple RMI calls from the same site. So the question then becomes: so group communication layer handles these threads, and the question becomes: how many receiving threads should we have? And how many client and server threads, how many receiving threads at the server end, how many receiving threads at the client end, and you can give the same kind of arguments that you want to keep the messages in order. You don't want to make, destroy the order that the sending guy created for you. Okay, and clients can have one thread per application subsession. So the clients can. So that's what should happen. And server is a little bit more complicated. What does the server do? It has a receiving thread. It receives messages, and what does it do with the messages? If it's going to do anything, send them across to other sites. So it's already got these sending thread, one sending thread per application subsession. So all this receiving thread does is put the message in the right sending queue. So that it doesn't make sense to have more than one receiving thread at the server. Okay. So you see this in this picture. This is the implementation that you guys will use, and you see that there is a single receiving thread in the server. Okay. There is one one thread per subsession. Okay, so the IM has one. If we had editor subsession, it would have another one. There is one there's one thread for the sender. Okay, so this is when things get complicated. The system I'm describing to you does both peer-to-peer and relay communication. Okay, so what it does is it creates one thread for the server to send messages to the server, if you're sending messages through the server. And then it creates one thread per user, per peer, okay? So that messages to different users don't interfere with each other, okay? So it doesn't know whether you're going to do, it does know actually whether you're going relayed or not relayed. Okay, but you have to go and send all the join calls to the server. So even in the peer-to-peer case, it will create this thread. And in the peer-to-peer case, it will also create one thread per peer. Okay, just to have the ordering and the consistency constraints both being met. Okay, so you're seeing that, and then it's got one receiver thread per application session. Okay, so this is all very concrete how things work. Okay, questions? Okay, let me revisit the threads situation. Okay, I explained threads to you, and then Nick pointed out that there was, we wanted to reduce the latency to other users so that we shouldn't have to wait for messages to go to to the previous user before we can send a message to the next user. Okay, so in general, a process is sending messages to n users, and if we do them serially, then the last user is going to have to wait for all the other users to receive the message and send ACKs back. Okay, and I said, look, we really have a thread per user, and I kind of waved my hands. And I'm going to show the stuff now in slides to just make sure things go fine. And in fact, when I started looking at my code, it wasn't implemented perfectly, so I actually updated the code to make it correct. Okay. So what's really going on here? We have to consider the threads we create under three conditions. What threads do we create in the client when it's using relayed communication? What threads do we create in the client when it's using peer-to-peer communication? And what threads do we create in the session manager? Okay, so there are three situations to consider, and this is a non-trivial thing. And we said that, look, we want to serialize all messages that are sent to an application subsession. So a particular client can be in multiple sessions, Ideally, every program should be in one session, and you should just run different programs at different sessions. But you may imagine having one process that is part of multiple sessions. Okay, so at the client end, we're going to serialize messages to each application subsession. Okay, if there's another application subsession, that can have an independent queue, which doesn't interfere with our queue, so we can have concurrent threads there. Okay, that's what I told you last time. And if we're doing relayed communication, that's all we need to do, because we are not sending messages directly to peers. we are sending messages to the session manager. So my IAM process, my IAM thread will send messages, the IAM messages to the session manager, and my editor thread will send editor messages, and they don't have to wait for each other. All my messages sent to the editor subsession should be serialized, should be go in sequence. So I want one to be processed. I want the first one to be processed before the second one. Okay, so that's all we have. We have these for each subsession. We have a thread. Okay. Now when we go to, so the application session threads send join and leave requests to the session manager, and also send the relayed messages to the session manager. Okay. Peer-to-peer, we again have these threads to serialize messages sent to that session. These threads also send messages to the session manager, but we also now have separate threads for each peer. So if I'm Bob, okay, I'm Bob, then I have a thread for Alice, and I have a thread for Kathy. Okay, so first I serialize the messages that go to the IAM session, and then I go and dispatch them to different threads for different users, so that messages to one thread don't cause to one user don't cause delays in delays for the other user. Okay, so if there's an editor there, now I have also a thread for Kathy because I'm Bob. Okay, and of course Alice is not in the session, so I don't have to create a thread for Alice. Okay, so clear that you have one thread per application subsession and one thread for each peer. Okay? And we'll see later that we can add delays. Okay, so when you guys do causality and operation transformation, you want to delay messages being sent to specific users. It's even more important in that situation to have different threads for different users. Otherwise, one delay would cause delays. Delays for one user would cause delays for the other user also. Okay. So peers sending threads receive messages from the application session threads and send messages to peers. Delaying messages based on delay parameters. That's exactly what I just said. Okay, questions? I've said this before. I just have pictures now to show. Now I could, if I'm being efficient, have only one thread that sends messages to Kathy. I don't have to have two different threads. Okay, this thread could be serviced by, because the serialization of messages is occurring here, so they'll arrive at the right order if I just had one thread. But it's just more modular for me. There's one module that's created for each application subsession that forks the threads. It's just easier for me to create threads for different users. Okay? And like I said, an application a process should be only part of one session. If a user is part of more than one session, the user should really have different processes. Okay? It's like in Chrome, each tab is a different process, and that makes things more fault tolerant. Whereas in Explorer, each tab is a thread, perhaps, with one big process. Okay? So you should really use the Chrome approach for various reasons. Okay? My session server, it has a thread to send messages to each subsession. You could also have separate threads for each user. Okay? That would make sure that delays caused by sending messages to one user don't result in delays for another user. And similarly, you could have threads for other users. Okay? Now that's what you should do in an ideal system. But this library that I'm talking about does not create threads here. Okay? It's maybe I was being lazy, but the real reason was that, look, if you really care about feed through to the other user, you should, and that's something you care for when you're sending telepointer positions. Why are you doing relayed communication? Just do peer-to-peer communication, and then you will get separate threads. The fact that you're doing relayed communication implies that latency is not such a big issue. But the real moral here is that all this, this thread design really resulted from the fact that we're using a synchronous IPC, and which is RMI in my case, and that's what was causing all this pain. And of course, I wanted to code easily, that's why I did that. But the moral really is that you should not use synchronous IPC for collaboration. Okay, which is kind of an interesting result. But a long time ago, in the 70s or early 80s, I believe in the late 70s, somebody wrote a paper saying that synchronous IPC with threads is equivalent to asynchronous IPC without threads. Okay, you just fork threads in one case. Okay, but when you get down to this scenario, we see that performance can be a real issue. Even if thread creation is cheap, performance can be an issue for feed-through, and they weren't thinking of that. And that's one of my favorite papers. It's by Lauer and Needham. It's one of the classic operating system papers on the duality of operating systems. And what we kind of find out is that, look, there is even with all these threads, we have to wait for round-trip delays before we can send the next message to the other part, to a particular user. And that really does cause problems with telepointers. I've tried that out. So there are issues. And just to make this all very concrete, what do I have here? I have the session manager threads. I have Alice's threads. Alice is joined as a P2P member. Bob is joined as a relayer member. So we have different threads for the two of them. And here's my, I have a receiving thread. Okay, I talked about that earlier. I have one sending thread per application. Okay, which happens to be per application per session. So that's my thread in my server. I have a receiving thread in my client. I have an application session sender thread in the client also. Okay, plus I have a thread for my peers Bob and Kathy. Okay, so this really does work, at least as of Saturday night. Okay, when I changed it. Actually, it worked earlier too. It was just the naming was a little different. And Bob has no peer senders because Bob is using relayed communication. So in Bob's case, this particular thread is sending join, leave, and relayed messages to the session manager. So we don't need peer threads. Okay. Questions? Nick?
So I'm trying to understand. So Alice is connected. So Bob is connected to the session manager.
They're all connected to session manager, but Bob is using session manager to also relay messages.
Okay, and Alice is not.
Alice is doing P2P.
Directly Bob.
Yeah.
And are they both equipped to receive messages in either fashion?
Yes.
Okay.
In fact, you just change the arguments to your method, to your main, and things switch. Everything else is same.
Okay.
If you remember, there was a lot of arguments. One of the argument was, how are you going to join the session? So that's a late binding, which is really nice. Okay. Other questions? Okay, just to switch topics a little bit. Way back I said to all call is motivated by the fact that we want sequencing of actions, okay, across the network. Does it make sense to have the to all call when we do peer-to-peer communication? We're getting no ordering.
Well, even if it's peer-to-peer, we might want to send a message to everyone in the network.
So we want some work to be done by everybody, right? Including everyone means us also. Others means everybody else. To all means everybody else and me. And when we're doing peer-to-peer, we don't have the situation where the message will come back to us from the server. It just means what? What does it even mean to do to all in peer-to-peer case? When we send a message, the result of the message is in the other side, what happens? A callback is invoked. So what will happen now? The same callback gets invoked in us also. So this is how we can get feedback. Well, it's not really feedback from the server, but it is some kind of feedback that the underlying layer got it. So does that make sense at all? Okay. Both local and remote feedbacks in callback that way. We don't have to have one piece of code that does local feedback and another piece of code that does remote feedback. We can just put that all here. But the danger is that if we later go to relayed communication, we'll have to wait for the message to come back from the server. Okay, so if you're going to be flexible and you're going to say that, look, we can either do relayed or we can do P2P, then don't use to all, use two others, and have your code be partitioned where one piece of code creates local feedback and one piece of code creates remote feedback. Okay, so I have really looked at the concept of group communication. Okay, and I've looked at some choices. I've kind of hinted what choices you're going to have been made in the system you're going to use. But now what we're going to do is look at that particular system, which I'm calling group messages. That system could be created on top of any of these underlying primitives. Okay, and it so happens that its design is independent of the underlying layer, but its implementation uses RMI, and that really means that, and the reason I did that was because I was lazy. Okay, I wanted to use a high-level layer. This is a remote procedure call, but it's synchronous. That means our remote feedback is going to be influenced. Okay, it's not going to be as fast as we'd like it to be, and there was really no convenient RPC available at that time for asynchronous. So actually later I built my own RPC system that is asynchronous, and Google also has asynchronous RPC, but that involves the web. It's on, as far as I understand, it requires you to use the HTTP protocol. So, but this was done before I built my own system. And I also wanted to create a layer that you guys can look at and understand. If I go and create a layer that's built on top of some other layer I built, then it'll be harder for you to understand the group session there. Okay? So motivation, but this motivates why you need asynchronous RPC, because our feed through is going to be bad when we send a series of messages to another site. Okay. So we're going to just look now at an example. We're going to take that old echoer example and create the multi-user version. And this is the one I showed you in the code that I'm giving to you. It's not the code in the demos. So we're going to have now not just an echoer program, but we're going to have a program for each user, okay? And we're going to have a program for the session manager, okay? So you now know why you need these 4 entities. And let's go and see how this is implemented, or at least let's not go and see all the details, but see enough details to show you how this system I'm describing works, what the API is. Okay, I've talked about the API in very abstract terms. Now you get to see it as Java methods. Okay. So here's my session manager starter. Okay, and you guys, the first thing to notice is this funny stuff here, tags. So this @ sign here. What does this @ sign typically signify in Java? For those of you who are more familiar with Java. Annotations. So the tags annotation, is that something you've seen before? So that's an annotation that I've created. Okay, you can create your own annotations. Okay, that's an annotation I've created. And what am I really saying here, based on how it's used? What am I really trying to say? I'm putting it the header of this class. Okay. So what is an annotation exactly? What is the purpose of annotation? Is it like a comment, or is it a comment?
It's not a comment. It's used by other classes to figure out what this class will do.
So it's a way of documentation, like a comment.
Yeah, but it's a comment. It's not a comment. It is actually. So, I mean, I think the compiler uses it.
So okay.
For example, there's an override annotation which would force you to override a method from.
So the compiler uses it,
Yeah.
and even runtime runtime can use it. So comments disappear once the program is compiled. Okay, whether your program gets compiled or run does not depend at all on your comments. Maybe some people will argue that it should. Okay, and annotations are typed comments. Okay, so I told you guys earlier that comments, comment as you feel like. I'm not going to look at the comments and comment to satisfy yourself, not satisfy me. But but these annotations you will have to put in to satisfy me. Okay, so what are they saying here? This program is an example of a server. Specifically, it's a server that's a session manager. Okay, and I'm using some standard terms here so that I can look at your code. And if I'm going to run it myself in a tester, I need to find your session manager, right? I can go and ask you to name it some ways, but that constrains your creativity. So I say name it as you want to, and I'll just look for the tags, and I'll run the program that you say is a session manager. And for your IM assignment, I'll look for the session manager that you've created for IM. Later, when you go and create your operation transformation assignment, you guys will be creating a server into which you'll inject your own code. Okay? Because for operation transformation to work, you have to do some work, application-specific work at the client end, and some application-specific work at the server end. And there is a way to inject code into the server, and we'll talk about that way when we talk about operation transformation. Okay? So all these three tags are telling me what you're doing, telling me as an end user to try to read your stuff that what you're doing. You don't have to go and put a comment. And as it's telling my testing program information needed to run your tests. Okay? So annotations provide typed comments like traces, but are passive. Okay? So traces actually generate output. These don't generate output. Okay? But both traces and this provide you with information. And other than that, when you run this program, you create an instance of this generic session manager. Okay? That's the goal of this program. Okay? You have to do a few things. You have to create an object. You have to go and this is a program that's created by me. So you don't have to go and write this program. You just run this program. Okay? Sorry. These two things are created by me. This is also created by me. But if you are going to use some different tags, then you'll have to create your own starter and put your tags in and then run the program. And if you create your own program, just make sure you instantiate this object and you then register it with the RMI server. Okay, so I told you this is built on top of the RMI. RMI has its own server. So this server is a client of that server. Okay? And this server actually starts that server up. Okay, questions so far? So this is my Alice starter now. Okay? This is your client. And now I'm asking you guys to go and say, okay, I'm implementing the IM application, okay? And I'm client 1. Okay? So I have tags for client 1, client 2, client 3. And I'll ask you guys to demonstrate, to support at least 3 clients or 4 clients. I'll give you a number. And then you have to go and say, this is my program to start client 1, this is my program to start client 2, so that I can start those clients. Okay? And so this is a tag that just says that. And as it turns out, client 1 goes to Alice. Okay? But you don't have to care about it. Question?
Oh, I was scratching my head.
Okay. Now you notice, if you remember, so when you run this, you start an IM client. Okay? And this is the client 1. And notice I used to have, I showed you very abstractly this join call, and this join call has all these arguments in it. So this is where the arguments are being given. Okay, it's saying here's the session server host, here's my session name, S1, here's my username, here's my application name, and I'm also saying whether I'm communicating directly or relayed. Okay, so all this stuff is real.
So why is this in an array instead of being passed as arguments to the launch method?
So what's going to happen is that I'm running this. So here's the launch method, right? And I'm passing these as arguments to the launch method. So this is the program, the shared symmetric program we talked about. Remember that all the clients will run one program, and they'll just provide different arguments. Okay? And that program has a main in it. And that's a program you can run independently. So I'm using the same philosophy as main to pass these arguments.
Okay.
That's all that's happening. Okay, rather than having separate arguments, maybe that was a better choice, but I started off with the main idea, and then I started off with having different programs that call different mains. Okay, and the reason why I went to the latter was because I wanted to do this testing, and I don't know what combination of parameters I should use for your generic program, so I just decided that you guys create these launchers and provide your arguments also. Okay, so let's look at session server host. Anybody here has written a distributed program in their life before? So this is going to be a great learning experience for you guys. How do you think I would specify a server host? I mean, what do you think? How does one specify the host? Through some number, through some IP address? Or the domain, okay? And when you're running on your everything is running on your own computer, what would you give there? Local host. Okay. Host specification. So by the way, you can find your host name in any system. You go to Mac, you go to Windows, you go to Unix, just type host name, they all have the same command, it'll tell you your local host name. Okay? You can either use this or you can just say local host. Okay, and the nice idea about local host is that I can take the same program, run it on my laptop at home, run it on desktop, I don't have to go and check it. Seems pretty easy, right? Simple. Okay, so let me tell you something complicated that can happen. It happened to me. It took me forever. Okay, I start my session manager server. Okay, it says, okay, I've started, I've registered with RMI, I know it's running. Okay, I run Alice, IAM, and I get exception connecting to permission denied. And I found this error in a hot Indian summer day. And you sweat because of the heat also, and you sweat and say, what did I do wrong here? Do I not understand RMI? Do I not understand, did my multicast layer fail here, or did my application program fail here? And if I go and look at this, what do you think this is saying? I mean, if you get this, what is this indicating to you? That somehow, yeah. Right? Somehow there's no permission to communicate between the client and server. That's what it's saying, right? And there is an Java policy. There's a file that you have to create, which will give you permissions. Okay, and I played around with that a lot, and .java.policy, I think, and nothing I could do in that would cause my problem to go away. And the same program I had run earlier and it had run. And something had happened and I had no clue. So, how does one solve this problem after sweating out a lot? Let's look at this number here. If I'm running in a home computer, do I expect this as an IP address of my local computer? It'll be some 191 something. Sorry? So where did this number come from? That was my key to solving the problem eventually. I said local host. Promise. And if I go and do ipconfig, I see this number indeed. And I also see another number. Anybody? So that was the key. I was running the Cisco VPN. Please don't run the Cisco VPN when you're doing your programs. Okay? And that basically is, your local host meaning changes when you're running Cisco VPN. Okay? So, and the error I should have got from the underlying layer is say that there is no server at that end. My server was running on my computer, not on that computer. It says access denied, which is what it made me go to, all the Java policy files. Okay? So this is why you need good error messages also. Maybe that layer is trying to avoid security issues, but you sometimes don't want to tell the client whether the process exists or your access was denied. So maybe that's why it's doing that, but it should have just said, look, there is no such process. Okay. And by the way, the error messages become a little different if I give my local host name rather than saying local host. Okay. So that's my big warning to you. Okay. So I've got about 1 minute, and what I'm going to talk about is pretty mundane stuff. Just the concept we've seen already, but just the API. So let's just go through it a little bit. So the question is, what does a shared symmetric program do? That's the next problem. Next question. Okay. And we looked at the session host issue. So in there, you have to make a join call, as you can imagine. Okay. And you have to create it before you can make the join call. You have to create the communicator. So this is what creates the communicator object. Okay, this piece of code. And so now I have this code here that I can use to go and do things with. And I want to just say that, look, this again bad design to some degree, and I want to change it at some point. Just go and look at the code for create communicator in the project, and just use it in your code. I should have really put this in as part of the library, and I just some decisions I made later, and I just put it in the code. If I get chance, I'll put it in the library also. But for now, I don't like this because cutting and pasting is always a bad thing. It means that you can abstract out. So just copy and paste this code to go and create a communicator. Okay? But you can see that logically, I need to create communicator from the arguments I pass to the main program. So that's all I should be doing. You shouldn't care about what it really does inside. Okay? But it uses a couple of factories. It decides whether I'm going to use the direct communicator factory or the relayer factory and instantiates that, and I can easily encapsulate it out. Okay? And add collaboration functions. What do you guys think this is doing? This is clear. It's doing the join. Okay? Which is just saying join. What could this be doing? So when I join, I'm saying, look, I want to join, and also I'm saying I'm ready to receive join callbacks. So before I join, I better go and tell the system what my callbacks are going to be. Okay, just as when you guys put callbacks in your, so this is basically saying add callbacks before connected to server. Okay, and the callbacks you add are up to you. Okay. And at this point, after that, we invoke call on server. And what's left is the two others call, which is what you'll be using. And the question becomes, what do you send to the other party? You need to send some data structure. And the data structure you're sending is a data structure describing your operation. Okay, so you're not making RMI calls saying this is a procedure, these are the arguments. You have to go and take a procedure, the operation name, and the arguments, encapsulate that into an object, and send that object across. Okay, so that's this. And that object better be a serializable object. Okay, and if it's not serializable, RMI uses this particular tag, serializable tag, to decide what variables of an object it will send, and only those variables that are declared in classes that are serializable are sent. Okay, so just make sure that the data structure you send is actually serializable. Okay, and if that causes any confusion, there's a lot of Google documentation. You can just search the Google. I've written a lot of stuff on serializable, but that's done in a very it's done in an academic way where I describe all the concepts. But just in terms of making it work, you'll find enough documentation. Okay, so you pretty much know right now how to send messages, how to join a session. You can understand the code. I haven't told you exactly what kind of I haven't told you the architecture of your application, but you can try to think of it yourself. I'll talk about that on Monday. But if you want to keep busy till Monday, I would really encourage you to go and, based on what you've learned today, start changing your application. And if you made some wrong decisions, we'll correct them on Monday, but you would have learned as a result. Okay, so like I said, I'm a little uncomfortable giving you all the details I'm giving you, but as I said that those details make sure that you guys do the right thing also. So the way to really get the best of both worlds is to first think of them yourself and then say, aha, I did it right, or no, I didn't do it right. Okay, so there's more than one way to implement the user interface that you see on the video. There's replicated and centralized, and I think you guys pretty much are going towards the replicated. I mean, I think the replicated architecture is in your mind, and that's what I want you to do. But if you implement the centralized architecture, that's fine with me also. The replicator will be easier. Okay, so what these terms mean, we'll see last time. But just try to go and figure out how to implement, and you'll come up with these two choices in your head. And you really appreciate these architectures better. Okay, so the assignment will be due not on next Wednesday, but the Monday after that. Okay, sorry I took extra 5 minutes, but I wanted to finish this stuff. So let's just review questions? Question? Okay. Let's just review what we did last time. So I pretty much told you the workings of the library you'll be using. Okay, I haven't told you the various ways in which you could use it to build your application, but the semantics were given to you. And I first looked at things in a very general way. Then, what would you do if you were to build a multicast library? And then I showed you exactly the things that are in that library. Okay? And we were getting into the details of the API when I left off last time. And we were just taking an example application to illustrate the library. And the idea is that you're going to have your session manager process, and you're going to have a process for each user. And each user's process is going to execute code that you wrote and execute code that the library provides. Okay, so the library provides you with a server and a way to access from your process the server. Okay, so that's the communicator object. And so we're going to have 4 processes, and this process is going to run both the. And we talked about how to start the session manager. There's just some boilerplate code that you just run, and it starts. And I mentioned last time that you should put tags in. I forgot to add this stuff in the assignment, so I will edit the assignment to tell you you should put the same tags that you see here essentially. And this program will create the session manager, which is generic. It's independent of the IAM application. And then we saw how to start the each process in the each user process in the session. And again, we put some tags, and we're going to use, all user processes will use the same program, and they will just pass different arguments to the program. And these arguments could be provided from the command line. Okay, that was what was intended originally. Or they can be provided by a specific program that you write. Okay, so you don't have to remember all the command line arguments. And that's what I recommend you do also. Okay, and that's something I'll put in the assignment. So, so the idea is that at this point you have an IAM member process running. And the next question is what really goes on in this program, which does the real work. And it has to do whatever the echoer program was doing originally. It has to do the regular, the UI stuff. And the code I've got is basically subclassing of the echoer code. Okay, but this is the interesting part from the distributed or collaborative point of view. You're going to use a local object to communicate with the session manager, and you have to instantiate the object. And this is what you do to instantiate it. And you just basically pass it the arguments that defined that particular user, and you get back the object. And then you go and you go and compose your application the way you were composing your echoer application. Okay, so you create the model and interact it together. Okay, that's something we don't have to worry about right now. And ultimately, you will ask your communicator to join the session manager. Okay, and when we talked about collaborative applications, we said a collaborative application provides many functions. Okay, it provides session management. This is being done for you right now. It provides coupling. It provides awareness, perhaps. It provides access control, perhaps. It provides concurrency control, perhaps. Okay? So as we go along in the course, we'll be adding more and more functions. But for now, we are just going to do coupling. Okay? But I have this generic function that says add collaboration functions, and that function right now will just add coupling. Okay? And the way you do coupling is that you have processes talk to each other. One process sends messages, and the other process defines callbacks. Okay? And these callbacks are invoked automatically for it, and you should register the callbacks before you do the join so that they're ready, because as soon as you do the join, a join callback may be called in case you want to provide join session awareness, plus somebody else must send you a message for which you need to have a callback. Okay? So just as in your GUIs, you first created the whole frame and then you set visible. Okay? You're basically setting up everything, and when you do a join, you're making yourself visible as a process to other processes in the session, to the session manager. So you better have things set up. Okay? So that's the order in which you do things. And the do join is just calling join method and communicator, and we can override it, and that's why I put that in a separate method. So that's the instantiate local group communication library. At this point, we've got something to communicate with the session manager, but it hasn't really communicated. And like I said, I'll make that part of this method as part of the generic library. And you add callbacks before connecting to server. You invoke call on server, and at this point, you are visible to the rest of the world. Okay, you're connected. Okay. That's the main conceptual thing here. And then the question becomes, okay, how do I actually send messages? And we know this is a multicast. We can just say send message to others. And that's what this is all about, the two others. And the question is, what is the message object? Okay, now, if you're using low-level functions, you just send strings or bytes as messages. Okay, but we are using high-level abstractions. We're in Java. So we want to be able to send objects defined by us, not just strings and bytes, but just arbitrary objects. Well, not quite arbitrary objects. Arbitrary objects might contain pointers, and we don't know what to do with them, perhaps. And they may contain pointers to local objects that can't be sent across to the other side. I told you last time that when an object has pointers, we just go in, follow the pointer, get the whole data structure, and create an isomorphic copy at the other end. Okay? But if that data structure has some site-specific data information, then you really can't send it. Okay? If it has a pointer to a window, what does that mean on the other side? Okay? So we have to go and send. So what is the kind of object you can send? In this case, we're sending this list edit object, and that list edit object we have guaranteed to be a serializable object. Okay. So if it's serializable, then you're saying, look, sending its variables across is no problem. Okay. And serializable is an interface, and you don't have to really implement the interface. You just have to say, I implement the interface. So it's really a tag. It's a bad way of doing things. This was invented before tags were invented in Java, okay, before annotations were invented in Java. So it's just saying, look, my variables in this class can be sent across, and the variables of all my subclasses or subtypes. Okay, because if a type implements an interface, then a subtype also implements the same interface. Okay, so that's what you're saying. And you can have transient variables, which are variables that aren't sent, but you don't have to worry about them in this project. But there's a lot of details about serializability, but this is what you really have to know. Okay? So that's one concept, that you're basically taking your data structure with pointers, you're serializing it, you're converting it into something that can be sent on the wire, and then it will be deserialized at the other end. And that serialization and deserialization is done by magic. Okay? And it's done not by my layer, but because I'm built on top of RMI, and RMI is built on top of the serializable layer, so we get all these benefits. Okay? I'm not doing anything special here. If something breaks, don't fault me. Okay? So that's what this whole text is saying. Now here's another thing that I want to talk about. So notice that the operation, what we really want to do is send information about this operation. Okay? An operation has a name and arguments. And what we're doing is taking this operation with its arguments, converting that into a data structure, which is serialized. Okay? So what you had was, conceptually in the program, you had the observable and add operation with some arguments created. You want to go and inform the other side that an add occurred with these arguments. What I'm giving you is a to others call or a to client call that takes a data structure. So what you have to do is take an operation and transform that into a data structure, which is then serialized. Okay? This process of converting an operation into a data structure is called marshalling. Okay? So if you think about what happens in a local procedure call, the operation with arguments is converted into a data structure that is popped on your stack, and it's called an activation record, if you know anything about compilers. Okay, so that's basically a data structure on your stack. Rather than a stack record, what you do is send a data structure on the wire, and that's called marshalling. Okay? And at the other end, that data structure is converted back into an operation which is pushed onto your stack. So this way you can invoke a call from your procedure at one side that results in a stack record being pushed on the other side. Okay? And so there's this long process, and from again, I don't want to get into the details of that. When I teach distributed computing, we actually implement this in a very generic way. You have to now implement this in a very specific way. You have to say, look, these are my operations, these are my arguments. I'll convert that into a data structure. This is what I use. You're welcome to use another data structure. You're welcome to borrow the one I have. And that's what I'm going to pass to others. Okay? So this marshalling and unmarshalling. Okay, questions about that? So you take your operation, convert that into a data structure. That's marshalling. That data structure gets converted into a wire format, something that's sent across the site, and that's called serialization. Okay? So at the other end, you have deserialization and then unmarshalling. Okay? So normally, if you use RMI, the marshalling and unmarshalling is done automatically for you. But we're using multicast. And building a multicast RMI layer is tricky. I've done that in another system. But you can't just take RMI and change and put a multicast layer on top of it. You have to change RMI because RMI is blocking, and it sends things only to one side. There's many reasons. Okay? So for that reason, you have to do the marshalling yourself. If you were just using RMI and sending it to one other side, that would be done automatically for you. You cannot build a multicast layer on top of RMI that does marshalling. You have to change RMI, which is what I've done, like I said, in another library. But that library is beyond beyond what I want to talk about here. Okay, so what you're going to get at the other end, you have to somehow receive the data that was sent by the sender, and we're not going to make an explicit receive call like I spoke earlier. We're going to just define a callback, okay? And we're going to say, communicator, please add a peer message listener. The message may come from the session manager, may be relayed. We in fact don't even know how the other side is sending its messages. Okay, but the message ultimately was a peer. So we're going to say, please define, make this history in coupler a peer message listener, which means it must have an interface. Okay, and so that interface will define some method that is the callback. Okay, and this is the method. Object received is the method that is called back in this listener, and it has the message and it has the user who sent the message, just in case you want to use that information. Okay, and what does that do? Well, it goes and sends that, it processes that, and we know what to do with the list edit. We just have to go and update our model. That model will update our that's what happened in our architecture. We'll talk about that in depth. But from our point of view, we see now how that whole communication occurs. That you send a message, and the other side defines a listener that will listen to that message. Okay? So that's how data are communicated from one side to another side. Okay? No new concepts, just the API. So that's the header of the message. Okay, now I'm doing message instance of list edit. This might seem silly, right? I'm expecting a message from the sender. The sender sent a list edit, so why do I have to go and do this extra check?
For fault tolerance, so that our program won't
bomb
do
if
unexpected things if we don't receive list edit. For forward compatibility, if we define a new version of the sender that can send other things, we don't want the old version of the receiver to not be able to handle it.
And so, firstly, if we don't trust the sender, we want to do fault tolerance. We want to report an error message. Okay. Of course, Java will throw an exception and give us a message too. If things change later, we have my new list edit, then we want the old guy to still work, perhaps. Okay. And actually, the real reason is that we might have more than one kind of receiver. Okay, we might add new kinds of messages, which is kind of what you were probably saying when you add that. You might send an access control message also. So there may be many, between two processes, there may be many channels. One sending access control messages, one sending coupling messages, one sending concurrency control messages, and there's only one physical channel there. So you basically define different kinds of listeners that go and say, okay, I'm expecting this kind of message, so I'll process that message, and I'll leave all other messages to other kinds of listeners. Okay, so in the communicator, you can add multiple peer message listeners, not just one. You can have 5 different listeners. Okay, so can have multiple listeners. And this is where you're doing unmarshalling, right? You're going and basically taking the message and then and calling a procedure, passing the message, passing the data, and that will call other procedures. So ultimately, we've called a procedure in response to that original message. Okay, that pretty much shows you how to use the API. We've seen how to send messages. We've seen how to go and receive messages. We've seen how to join sessions. Okay. What we haven't seen is how to do a join callback. Okay, so when somebody joins a session, we haven't defined a callback because in our application, we didn't need it. Okay, all we do is join the session, and then whatever message comes in, we go and display it. We don't go and tell the user, so this Alice has joined, Bob has joined. We just haven't done that. Okay, so let's just go and extend our application to see how those join callbacks can occur and what they. Okay, so what we had was 3 different programs that were symmetric, and they just joined the session. Somehow all users knew when to join. Okay, they all decided at the same time to join, and they were in the session. And that's a constraint I put on your assignment too, that you can assume they all know when to join. You can assume that everybody's in the session before the first message is sent. Okay, there's no latecomer. That creates other kinds of issues. And but we could join when we know someone else has created and joined session. Okay, that's what typically happens, right? You say, okay, you often in fact in IM sessions you get an invitation to join. So to see how that kind of stuff can be implemented, we have the API to do it. So there's no awareness. So firstly, we knew when to join. That was one problem here. We also did not have any awareness of out-of-band activities. Okay, so out-of-band means whatever is kind of irrelevant to what the product we are creating. So the product we are creating is a history of messages. Okay, in this case, and signed by the user, so that we know which message came from which user. So there is some awareness, but that is part of the coupling semantics. That's part of what goes into the history. We have no other information. We have no information other than the history. So let's go and create a different version. I motivated this a long time ago. So I said, look, David can just join the session without joining any application in it. So they give null as the application name. That means they're just snooping. They're just listening for messages. And then David's process that's listening to these events can then go and fork off processes that join application subsessions. We talked about that last time. Okay? And we'll see how that's exactly done now. So now I'm going to have Bob and Kathy will still know by magic when to join. Alice will use a special kind of joiner which doesn't really join the session. It snoops. It listens for somebody else joining, and when it finds that somebody has joined, it goes and joins the session. So it doesn't do it prematurely. And also, this process will go and print out everybody's join and leave activities. Okay, and I mean, actually, it does. I think it just prints out the join activities. So that, look at the UI. So here's the session manager. It started. Okay, and I put tracing on to show you what's happening. And Alice's joiner has joined the session. We see that here. It's joined with a null argument. Okay, it's not giving you any prompt to enter text because it's not an IAM application. It's just a snooping process. So it's session aware joiner UI. So no prompt. This is not the IAM user interface. So Alice, this is the situation that Alice has joined the session without joining any application. Okay? Questions in the back? Okay. Next, Bob will join and says, okay, I'm starting an IM session. Okay? And at this point, Alice's process will say, oh, now I have somebody to talk to, so I will join the IM application that Bob joined. Okay? And let's see how that happens. You see that happening here? So this was a situation, Alice was all alone, snooping. Then Bob joined. Okay? Alice's joiner went and told Bob that Bob has joined. Okay? And that in turn created another process. Okay, doing I/O in a different console window that actually is like this process, and it can do the I/O. Okay, so that's what's happening here now. And this is the IM UI, and the session manager trace shows you that first the app null session was joined, then Bob joined, and then Alice joined in response to that. Okay, so we have 3 different join calls occurring, 2 with applications, 1 with just the null call. Okay, and now the key here is that we are passing null as an argument, and we are not using the program that everybody else was using. We're using a different kind of program that does different things. Okay, and that's this program. And that program now, in its add collaboration functions, it adds awareness. So it goes and says, communicator add session message listener, and it gives a object that will listen to that. Okay, so we had add peer message listener. Now you have add session manager listener also. Okay, if you guys want to build in your assignment something like this, which is a more dynamic system, which doesn't assume that everybody knows by magic when the others have joined, feel free to do so. Okay, and this is my session managed listener. Again, I have a callback. It takes certain arguments. It takes which user has joined, what application they joined, what session they joined. Is this a new session that was created? Is that a new application that was created? And what are all the other users in the session? Okay, what are the existing users in the session? So it has all this information. And what does it do? It first just prints out a message on the console saying so-and-so has joined. Okay? Then it goes and says, if the application is new and application has a name, that means there's a real application and somebody's not just snooping. Okay? Then I will go and join the session myself. Okay? So that's what it did. It said, look, if I haven't joined IAM before, and IAM is a new application that has been added to the session, let me join the session. And joining the session just goes and forks a process to join it, and you don't have to worry about how processes get forked. But a JVM can fork another JVM, and that's done all the time, and that's what's being done here. That it just forks another JVM that will actually do the IAM. Okay, and you can imagine it forking an IAM JVM or an editor JVM. You know, it can just provide you with a menu. It can provide the user with a menu of all the applications that are in the session. The user can double click on that to go and actually join. That's a fancier interface. This is just showing you the basic nuts and bolts you need to build something like this. Okay? Questions? So you've seen also the join callback. So this is the original program. So this IAM client launcher is the previous program that we're going to run. And this time we're going to provide the command line arguments that it takes. Okay, we are using that because we compose the command line arguments, give it to this process, and this process is forked off. The main is invoked with these arguments so that we can fork this process. Okay, so I have told you how I'm providing with this library. Hopefully, library does things for you that you shouldn't have to do. Okay, and this picture graphically shows you all the things you're not doing that the library is doing. Okay, and you know the code that the library implements, I can give that to you, and you can figure out what it does, and you might actually single step through it as you debug your programs. But if I'm going to tell you guys that please trace your algorithms, I should trace my algorithms also, right? So these are all the traceable objects that the library implements. There's 2 pages of it. Huh? So this is the first page of it. But to understand what I just explained, it helps to just go through these steps. Okay, so we know that we are doing things asynchronously. So the client will go and start a join, and at some point the join will finish when the callback arrives. Okay, so there is client join initiated, there's client join finished. And this is the communicator library. It itself processes these client joins so that it can keep its data structures consistent. Okay. Plus, if you as a program want to go and know about joins, then it distributes those notifications to you, and at this point you know that it's being distributed. We know that there's marshalling and unmarshalling going on. So you guys have to marshal your data structures. The library itself is sending data structures across. It's saying, okay, here's a join request. And it receives messages also. So there's marshalling going on there. There's not only joins, there's leaves. Here's the join, and there's some abstract classes here. We know we are buffering messages. Okay, so in a bounded buffer, so there's this message buffered step here. We are copying messages also. Okay, just so that people don't muck around with the messages we got. So there's message unbuffered. There's delays being set. The application program can go in, ask for message to be delayed, like I said. So this is when we know that it's been set. And not all steps are in here, and there are some deprecated steps. So so I'm not sure whether. I'm pretty sure actually that the same message is sent to all listeners. It's not as if a separate copy is created. So I'm not 100% sure what this message copy is about, but it may be some internal copies that it's doing. Okay, and there's some more operations that you don't have to do. So if you ever, whenever I provide my students with libraries and they have trouble with their program, they say, oh, it's the library's fault. Well, if it's the library's fault, this is all what you're getting from it, or getting from the library also. Okay, so it might fail. Hopefully, it won't. Okay, so it'll help you guys to go through this to really understand what's going on underneath, because I do want you to understand what kind of algorithm is going on underneath to make this all work. Okay. So we've done a lot. There's 99 slides in this slide deck. Okay. I can't summarize everything here, but the main points that, when we're doing distributed architecture, we have to worry about not only the object architecture in a process, but the set of processes that are communicating with each other. Okay, so there are two architectures to worry about. And the architecture you create depends on what kind of IPC mechanism you're using, and what about distributed communication layer. And we will come up with multiple architectures that provide different amounts of flexibility. And this, I'm going to argue that the architectures I've given you here, which involve the session manager and a relayed communication or not relayed communication, is as general as you would need in practical applications. Modulo the problems about authentication, that you just say, I'm Alice. There's nothing, it's not really authenticated. So we're looking at general architecture, and the library I'm providing you with is a library that's supposed to work for any collaborative application again, modulo the authentication problem. In theory, IPC provides the most general abstraction, but it's not high level enough. So what we've done is add multicast, because we have to add our own session manager, which you would need for any application. We'd have to do our own multicast, which you would need for any collaborative application. And in any application, you would have the choice of using relayed or direct communication. So you would have to build all these things yourself. And what we've done is motivated, with this general architecture, we've motivated a general library to support this architecture. And this architecture really has a session manager. That's what it differs. That's how this differs from a general distributed architecture. Okay, and then when you have sessions, there can be you can have a two-level session. There's the overall session. Then you can have application subsessions within it. And other systems have also tried to provide session functions, but they have not provided this distinction. They also don't provide choice between relayed and direct communication. And there's all, and the threading that I've talked about. So there's something novel here. In fact, just last weekend, I wrote a paper on this also, but I was developing this over the summer, and it just got accepted. So this is bona fide research. Okay. So we've got relayed versus direct communication. We've got all specific user, all multicast groups as various kinds of groups that messages can be sent to. There's synchronous versus asynchronous as an issue in any distributed system, and we talked about that here. So that's something you should know about. When we design threads, there's an issue of consistency versus latency, and how we've done the trade-off is an important lesson in what I talked about. Okay, so you guys will build your application. That's one part of your evaluation, but also you're going to take exams, and in exams I'm going to ask conceptual issues having to do with these concepts like this. Okay, so that's the assignments will give you a concrete way to understand these concepts. Okay, but these concepts are the main deal. Okay, there's symmetric versus asymmetric join possible. That does everybody do the same join, or does one person create the session and the other person join? There's the concept of serialization and marshalling. Okay, so there's a reason why there's 99 slides. There's a lot of stuff that we talked about. Okay, there's a notion of session awareness. That are you going to have session awareness in your application or not? Okay, so that's very generic. Like I said, we are talking about a general way of doing a general multicast library. Okay, and that is sufficient for you to do your project. In fact, I would like you guys to do it using just these concepts, but looks like all of you have waited, perhaps because of the missing package. But what we'll do next is look at narrower domains. Okay, so you can use this for various kinds of sharing, and we'll look at model-based sharing and window-based sharing, as you know from your demos the first day, and so that's sort of, and we'll build special architectures and abstractions for these cases. Okay, so how to build higher level abstractions